Good morning, dear friends of lightweight architecture. Welcome by the International Conference, Architecture of Lightweight Structures. I'm very sorry about the time shift due to technical problems. My name is Aleš Vaněk, and I will guide you through today's conference, which is organized by Department of Architecture of Faculty of Civil Engineering, Czech Technical University in Prague. The conference is divided into three main sections. It is architecture and structure, membranes and foils in architecture, and stories of realized structures. Now let me introduce the studio of membrane architecture, where we are now sitting, and the conference is broadcasted from here, and I will introduce by a short video.
Allianz Arena v Mnichově, Watercube v Pekingu nebo zastřešení fotbalových stadionů pro mistrovství světa. Jak tyto projekty vznikají, o tom se budeme bavit s Alešem Vaňkem ve studiu membránové architektury. Pane architekte, dobrý den.
Dobrý den.
Můžete nám prosím přiblížit, k čemu toto studio slouží?
Tento prostor slouží zejména k výuce a prezentaci membránových materiálů, lehkých konstrukcí. V podstatě jde o tenkovrstvé materiály, které se uplatňují například ve formě velkorozponových zastřešení u sportovních staveb, u dopravních terminálů, fasád, ale také je můžeme vidět jako prvky drobné architektury, nejvíce ve formě zastíňovacích konstrukcí.
A co všechno tady ve studiu najdeme?
Studio je vybaveno ukázkovými vzorky membrán a fólií, tedy těch materiálů, které zkoumáme, ukázkami studentských prací, poustrů a modelů, potom vším potřebným pro tvorbu fyzických modelů i digitálních. A tento prostor je také variabilně uspořádán, takže se tu dají konat akce v počtu 25 osob, jako jsou workshopy a malé konference.
A pane architekte, s jak velkými projekty se u vás studenti můžou setkat?
Studenti se zde mohou setkat s různě velkými projekty a s různými fázemi navrhování. Vyučujeme zde volitelný předmět membránové konstrukce, a také v magisterském stupni studia konstrukční ateliér, kdy studenti navrhují konkrétní objekt na zadané místo. A naposledy jsme například se studenty a panem profesorem Milošem Kopřivou navrhovali zastřešení historického Shakespearovského divadla dřevěného na výstavišti v Holešovicích. S kolegy také navrhujeme v praxi. To znamená, že vybraní studenti, kteří mají zájem o tuto problematiku, tak se s námi mohou podílet od návrhu až po realizaci na různých projektech.
Ještě mi povězte, jaký je o tento typ konstrukcí ve světě zájem?
O membránovou architekturu je v dnešní době ve světě velký zájem, jelikož používané materiály jsou trvanlivé, odolné a funkční a nabízejí inženýrům a architektům nespočet kreativních řešení.
A spolupracujete s jinými pracovišti s podobným zaměřením, jako je to vaše?
Tak v České republice jsme zatím jediným pracovištěm s podobným zaměřením, tedy od roku 2012, kdy studio vznikalo. A spolupracujeme tedy zejména se zahraničními pracovišti v Německu a v Rakousku a na profesní úrovni spolupracujeme s tuzemskými i zahraničními společnostmi, které se zabývají designem a produkcí membránových konstrukcí.
A ještě poslední otázka, pane architekte, na jakém studijním programu se můžeme s takovýmito konstrukcemi, s membránovou architekturou setkat?
Tak základní přehled a povědomí o membránové architektuře zde mohou nabít studenti bakalářského i magisterského stupně studia. A co se týká volitelného předmětu membránová architektura, tak ten vlastně si mohou zapsat i studenti z ostatních oborů na fakultě stavební.
Tak to zní skvěle. Děkuji za váš čas.
Díky za vaše návštěvu.
Naschledanou.
Naschledanou. Second contribution of the conference will be presented by Roithmayr, who is the founder of Formfinder, teacher and person who promotes lightweight architecture and lightweight structures in general.
Good morning, everybody. Thank you very much, Dr. Aleš Vaněk, for inviting me to this conference. I'm delighted to present you today architectural design of lightweight structures with Formfinder, our software tool. And my name is Roithmayr, and I'm working with Aleš since many years on this field, and we want to promote lightweight structures, and our goal is that we follow the legend of Frei Otto and this idea that everybody of us has to dig deep to fly high is driving us to new goals and will help us to enrich our world with this beautiful way of architecture building, the lightweight building. And on the left side, you see there's a film on Frei Otto with Dr. Simon Chu from Los Angeles, my partner. This film I would recommend everybody. There's a link on the internet, on YouTube, and also on the freiautofilm.com website. So please visit it, like it, share it. And now I want to start. How do we do our architectural designs? When we start sketching, the first idea is always something which is in our head, an inspiration, a goal, something that we want to achieve. And this smallest unit that we need to express our emotions, our feeling, can be described with a point, the smallest information unit possible. The point connected to another point derives into a line. And this line, you see, it's something which is connecting two statements, two information units. And when we come from this two-dimensional element into space, we need something which is imagination. And when working with membrane structures, we of course, when we connect 2 points, we don't have just a straight line. If you see this person here on the slag line, this person is standing on a cable, and due to the earth, the gravitation, to the weight of the person, this cable is sagging. And sagging means that we have curvature. That means cables, elements that are flexible, need curvature, need deformation to carry loads. And so to say, curvature is our friend. We need this curvature. And to express this in a small example, you see this is a small 3-point sail. There are 3 points on each corner, and they are connected with a straight line. That means a straight line with zero curvature would cause infinite amount of forces. And when we want to express curvature and we put it into relation of the surface tension in a membrane, we would reach here with a sag of 5%. This is the distance from this point to the other point. We would arrive here in 14 meters with only 70 centimeters of sag with a force of 3.6 tons. How to come to the tons? The kilonewton here describe that 1 kilonewton is 100 kilogram. It's one person, 100 kilogram, 1 kilonewton. So 36 kilonewton is 3.6 tons. So if you follow my mouse pointer here, and if I click here with the mouse pointer, so you see this, I click and I have here 10% sag, slightly more sag. This has the change, which is huge. The effect of changing the sag arises here with 50% reduction of the loads. That means curvature is our friend. Curvature helps us to reduce forces in tensile structures, and these forces are so crucial. So when we want to have a structure built, we have to deal with forces. And when we carry forces, we need to have a 4-point sail, because 3-point sails do not have curvature. So 1 point is the smallest information unit, 2 points is a straight line, 3 points describe a surface. So with 3 points, nothing can be properly built, which can withstand wind or snow loads. And in this case, a 4-point sail, when we have here to work against the force of wind, the wind wants to lift the structure from the bottom to the top, to the sky, and goes under the sail, lifts the structure. And if we want to reduce these forces, we need to have curvature as much possible from low point to low point. The next stage is, of course, here you see on the left side here, this is the snow load condition. Sorry, here, the snow load condition. My mouse pointer was a bit lower. This is the snow which is hanging in the structure, and the curvature should then be from high point to high point. The same is with the geometry and the force. The geometry 1 by 1 looks good. So if you stretch it, and if you completely stretch it up to 1 to 4, you maybe have to consider a change of the system. So up 1 to 4, it is needed that curvature is implemented into the surface to avoid flat areas. Flat areas are, of course, something that we don't want in structures, because flat areas cannot carry good loads. And as you see here, as Professor Jorens always mentions and states, nature does not scale. Therefore, we cannot just scale up a system or elongate it. Of course, a soap film or a curvature surface can be scaled, but when we scale it into the dimension, it doesn't work. Therefore, we need something which is helping us. And for this, we invented a tool named Formfinder, which is available to you, of course, in the university or also during these workshop classes. You see here an elder version, which is version 4, and it is linked together with other software tools. So it is Rhino, AutoCAD, SketchUp, all the environments that you are used to work with. They can be connected via DXF, DWG file format, or direct file linking, as you see here in the Rhino. So there's someone in the garden scanning with a PLK 360 scanner of Leica, for example, this area. They scan it, and then you can plug here your surface directly in here. And this is, of course, nice. And so I would say this augmented designer, it went already, so I show you something here, went further. My screen here. Surface here, the area, and when I scan this room, you see that this brought into 3D. And these tools, these apps are helping us to achieve a quality of design which is taking into consideration the built environment. And therefore you see this is an augmented data and designer to visualize the idea, visualize the concept to the client, to the owners, to the person who wants to use such a structure. And I think the tools are available, we should use them, and they should make our work easier. And as you see, we can use the elements around in space. Garden location here we use the most simple structure possible, which is a 4-point sail. And from this, it is necessary to calculate further. So you see here something that we developed as a performance checker. So you saw this sail, this 4-point sail, very trivial, very easy to use. And this is a fully online method that we use via the internet in combination with augmented reality, so that we can design proper sails with a correct force distribution, with proper geometry, and to create this beauty structure. So you see these corner points here, so A, B, C, D, E. These points are defining the structure. We have this curvature that we learned with about 10% of sag. This curvature is, of course, held in the corners with a corner plate, which we developed in this case with Forstrom of Sweden company. I want to focus a bit later on that. And then this sail is materialized again. And there are material properties that come from tests of Dr. Blum and from the laboratory Blum with Heidrun-Bögner parts from Dekra today. And then there is a small static calculation. You see the mast position. You see how the curvature of this sail has to be in an optimized way, and of course necessary to analyze curvature. Curvature can be done or can be implemented into the design process very early, because we need this curvature. And you see here on the right side, This is a cutting pattern sheet, which is, of course, not that we want to produce this sail with this cutting pattern. We could do this, of course, but what we want this cutting pattern layout to be brought back to the designer. So we want to give the designer design decisions that could help to achieve high quality designs, and these high quality designs are able to make designs from the early stage better. This is what we want. We want to bring as many tools, as high advanced features to the designer in an early design stage. Therefore, a proper design can help all the engineers later involved in the project to come to a project which is feasible, which is helping and creating value. So this is one part that is, of course, important, but this is just for 4-point sales. You can say, okay, it's a 4-point sale. They are able to do this. This is possible to make, like from software-wise, but it goes on, of course. There are more shapes, high-point structures, as you see here. And again, mentioning Professor Jorens, what is a high point? A point is, of course, not something which is the smallest unit in this case. A point can be a huge building-like structure. Or you see on the bottom left side, you see here, there is a circle on the ground here, and the high point here is also a circle, like a ring, a masthead. So-called it's a masthead. Then the next structure here is a 4-point squared ground plan, which has a corresponding high point also to the square ground plan. The other one is, of course, a loop. Loop is, of course, something which is a curve of constant curvature. And to describe this hole on the masthead as something which we have to design. Then we have also here a high point design tools. We can check the curvature here with all these tools. And today with version 5, which is available on the server, you can design here quite beautiful structures. You can combine these structures. As you see here, this mast is called rigid element. A client would say, oh, this is this blue thing in the garden, but this is a rigid element for a steel company. It might be a compression element, or it's a tubular element, which is with a steel quality, which has a coating and a color and so on. So all people involved in such a building process have different languages, and we want to join these languages together to a common sense and communication tool, which can be done via our website. So the glossary you can visit, you will see hundreds of definitions and descriptions. And here we have this protégé database where we put all these things together. And when it's ready, you see here a quite nice structure. So there's a video coming now. Can help the clients to understand what your ideas have been to the design. And when you have the design made, it of course comes to membrane architecture. I mentioned here Dr. Rainer Blum. He's working with this institute here, with the DECRA and Laboratory Blum. This was his office. And they are testing membrane materials. So you see the table here, a huge machine to tension the membrane, to test the behavior, and to learn how can this behavior of the membrane influence the geometry, the material and longevity. And therefore, Dr. Blum has been writing this book, the Blum book, and is here a German excerpt of the book. And you see shapes. All these shapes are in 3D available. We have this, of course, in augmented reality also. And if you visit our website, you will find a link to these models. There's description on building physics, on how to weld membranes together, how to stitch them together. And there's also Michael Wallin from Fostrom from Sweden, who we work with, and they are now able to weld steel on the membrane, which is of course wonderful. We can do corner plates of a high quality, we can calculate them, we can rely on the durability of such a connection. And here also for tents, for example, this is the architect Horst Dürr was working with a lot during the developments of Formfinder. And these plates can allow linear tubes to be bended. So if there's a tent, you can just put this badge on and you can curve a structure. So it's very fast to erect, very fast to develop. Therefore, the deep knowledge on details is necessary. So when you want to learn more, if you want to focus deeper, we would recommend to use, of course, standard elements to replicate. And this is also driving us. We made this Fostrom connection with the Eurostars project of the European Union. So we designed and we elaborated hundreds and hundreds of corner plates to make them better, to think what is the best corner plate. All these different angles are finding here per system point. And the result of this research was a series of corner plates. So this was one of the first designs. This corner plate here can take all the different angles that we need in this configuration. Like you can see here, this is the angle range. and we also got here this nice prize at the Expo, I think that was in the USA. And I think it's really necessary to point out that we have to appropriately respond to a new situation and not to respond to a semi-skilled pattern. And this is progress. To respond, to learn the situation, to understand, and then to change the thinking. This is what is our goal. And therefore, we want to become the best in our field. And this is the core idea of the master's program. So the master's program of the university in Vienna, Krems, is that we have postgraduate students coming to study further. There are several modules, and we want to recognize the future. So this small slide that you saw on the modules of the master program should just give you an idea that there are modules that people come, they learn, they go deeper, and what they want to do is to recognize the future. And to recognize the future here with our team at the Danube University in Krems, we have a team of dedicated experts ranging from building physics with Rainer Blum, with Jürgen Hennecke, an architect who worked on the site of Freyauto, Horst Dürr, who was head of the company Roithmayr, who built all the structures, or most of the structures in the beginning also with Freyauto, and Simon Chu, our partner in Los Angeles, he's dedicated to promote also Freyauto's work, his library, all the modules and everything. And also Vincent Sedlak, who collected over 40 years membrane projects, who's teaching dedicated to this field of lightweight structure. Then Dieter Ströbel and Jürgen Holl, who work, of course, from Technet with the Easy software. So Easy software is with Professor Gründig from Berlin, who was promoting or is promoting a lot of our work. Then Julian Linhardt, who is now a professor in Germany at the university. And we have people like from all over the world. There's Alex Heslop from the UK, Barbara Imhoff from Vienna, Peter Neen from Australia, Ami Koren, who's dedicating a lot, Peter Resch, Michael Schultes, Michael Seidel. All these experts, they are helping to promote that young people, that experts can come to achieve, to become the best in the field. So if everybody of us is the best in his or her field, then we can change the world. And to show you one project is one like an umbrella. This is a small project, but I just want to show you what comes out of these research connections. There's Julian Linhardt here with the ITKE. There's Knippers. Knippers Helwig was the office with ITKE. I think Jan Knippers is the professor there. And Julian Linhardt was making a PhD there on bending active elements. And one result or one side effect was here something that they found out on the parrot flower, that this flower is changing the bending effect to a rotation effect. That means the bird is sitting here on the flower, and the flower opens. And when opening this flower, the seeds can stick to the bird, and the bird can then carry these seeds around and flying. And there was Knippers. They built this pavilion in Korea, this Korean pavilion. And when you press on the lamellas, they open. So it's a wonderful effect that we used here to design this bionic umbrella. So these elements here are the lamellas. And when you open this umbrella, you see that the lamellas are here creating a kind of 4-point sail shape. And this is helping us to have more curvature in the surface and to reduce the loads affecting by the wind. And for me, it's nice that I show you here Formfinder 5 and the small video that okay. Just a moment.
Okay, läuft.
You see the video now? Sorry, it took a bit time to load the video. You see that this umbrella here can be located on the table, and the size can be described very easily. So you see the shape in the floor. And then this folder, which is on the Lightweight Structures program, we use this folder as a kind of, it's called picker. So we stick the 3D model onto this folder, and you can easily rotate this structure in the 3D space just to show the client how this can look like. And I think this is a wonderful way to share our 3D ideas with our clients. And you see this iPad here with the structure. This is one picture of the umbrella as it is. This is now the latest product that we have. It's a membrane viewer. And this membrane viewer allows to locate objects in 3D space and to share these structures with clients. You can find all this on the membrane.online website. And you see here profiles of Sahadid, Frei Otto. So we collected lots of information on projects. So there are thousands of projects. In the moment, we have, I think, 500-600 projects published. And we would be able to have 2,000-3,000 projects fully described here to be published. And at the end, I think there will be 8,000 to 10,000 projects that we want to share. So we are step to step releasing these projects, and we want to share them. And to show you a few examples of these projects, you see this is an iconic pavilion that I think it's worth to show. You see this beauty of the shape, of the curvature. And this curvature can only be derived with lightweight membrane structures. So curvature and the beauty in a structure is something that is already present in our structures. We don't need to bend them. We don't need to tweak around like with glass or steel. These things are really from itself in a nature form, in an organic shape. And this climate ribbon, for example, is something where we take into consideration that we increase the quality of our climate. The climate is affected. We can protect ourselves from the sun, from the wind, from the weather, from the snow, with membranes, with a thin, efficient, and long-lasting material. This is a nuvola, which is beautiful, an inside structure, highly curved, and this ThyssenKrupp tower by Sobek. And I want to show, why do I show this? I want to show that this shape of the membrane is not just something which is beautiful. This also has a reason. These elements is the scruton curve, scruton line, and this allows the wind to avoid, or not the wind, to avoid by the tower this alternating vertebral detachment. That means that these turbulences are produced by the shape of the tower itself. And this is something, but this is of course very much helpful. And so you see there are the amplitudes are much higher here on the right side to the left side. And this is what helps us in architecture. Also, another feature is not just the clever geometry that can help us to build better structures. Another logic is that there is the full climate building enclosure. This is something where Professor Blum is working on a lot, and these pictures are taken from Hubertus Beppinghaus. And you see, this is a pot, and we put on this pot a membrane or an infrared shield, and this shield is something that reduces the transmission or reduces the radiation of the heat. Then this was a project here by Sobek again, and here the coating was like worked out with Professor Blum, and this coating here reduces on the inside the heat. And with this reflection idea, there was developed further here with Jung a membrane, and this can be now used for facades. This can be used for all different structures, like a small thin film which is highly performant. It helps us to create a structure which can be a full climate building enclosure to any structure in the world. I think what is nice that we combined this here with wood. So wood and membrane is something which really fits together, and this wood is something which is like something that we can live in. It smells good, it tastes like, it creates a beautiful sound inside. You can hear it, you can smell it. So it's beautiful, and this is a quality we can achieve with wood and membranes. And therefore we made also a seminar in Italy on lightweight membrane architecture, including with membranes and also with wood. And to finish up this short presentation, I show you some work on Peter Cook. They built in Graz here this nice Kunsthaus, like the house for art. And you see an idea which was already by Frei Otto on the Öko house in Berlin. There is a kind of superstructure here, carried in this case by air balloons, and under this huge roof, this membrane roof, we can build light, small structures, beautiful structures with outlook. And so we have this protection from weather as a concept here, of course, as an artist's concept, but it goes further, that we have here this superstructure covered here with the membrane outside, and we are able to have our own individual habitat where we can live. And this is beauty, this is what we want to achieve. And so I feel enjoy the conference, and I'm looking forward to any question. Please feel free contacting me. It's mail@formfinder.at if you have questions, and I'm looking forward to your reply. Thank you very much. All the best for the conference.
Robert, thank you for your educational contribution, which show us great progress in the field of lightweight architecture. I know you for a long time, and you do really nice things. and I think, or to my mind, you would cover the field of lightweight membranes with many interesting contributions. So thank you very much, and I'm looking forward to meet you again on another conference. Thank you very much. Now I would like to present another topic, which is the Gridshells. I'm presenting this topic, so I have already introduced myself. So just I wish to enjoy the presentation. Thank you. Let me introduce my lecture on the topic Past and Future of Applying Gridshell. It was Jürgen Hennicke, a German engineer and co-worker of Frei Otto, who awakened my interest in the field of gridshell structures in 2014 during his lecture at a technical university in Vienna. At the time, it was a completely new topic for me, and in the field of lightweight structures, and captivated me with its simplicity on the one hand, and ingenuity and the possibility of creating double curved surface on the other hand. Unlike textile membranes, which are subjected to tensile stress, lattice shells are subjected to compressive stress but can interact to some extent with tensile membranes. A gridshell originated in ancient times around 5th century before Christ as a dwelling of nomadic tribes. These structures were very convenient for their ability to be quickly erected or dismantled and relocated. The lightness of the construction then allowed transport using animals such as donkeys, horses or camels, as you see on the picture. Nowadays, all over the world, we can see modern yurts as garden houses or even full-fledged dwellings, which testifies to the ingenuity and functionality of this structural system. At the end of 19th century, there was developed and realized first double-curved gridshell by engineer Vladimir Shukhov in Russia. This gridshell was made of steel pipes. The principle of gridshells is that we can, from the flat surface, make a double-curved one. The elements, by erecting, are bending in two directions and twisting, and the mesh of the flat surface, in starting point it's like in orthogonal way there are squares, and then when we erect the gridshell, then we get rectangles. There we can see some basic shapes made by research of Frei Otto using hanging chain model. When the hanging chain model is mirrored, then we can see structures or shapes that we can reach in gridshells. The structural system of double-curved gridshell was researched and developed in detail under the leadership of Frei Otto in Germany, whereby a unique and magnificent realization was created. It was the Multihalle in Mannheim, which has stood since 1974 up to today. There we can see a suspended net model, which is quite complicated, and we can see the size of the building, which is the height 20 meters and the span 60 meters, which is amazing. There is the interior of the space of the gridshell of Multihalle Mannheim, and this is the picture of today's condition. I did visit this structure in 2018 to see how it works. It's still standing after almost 50 years, which is great, and there we can see the whole structure. The membrane was covered the surface was covered by membrane, which was replaced after 8 years. So, and since the time the other membrane wasn't replaced. That means that this one takes place on the surface more than 40 years. The membrane is quite dirty, but there we can see some possible how to clean it. This is, I consider, it's made by snails. The building itself is not in well condition because they don't have much money to recover. So since 1974 is still the same wood used, and the structural main parts are supported so they don't fall. So you can see here again some supporting system. And there we can see Jürgen Hennicke, who guided me in 2018 during my visit in Mannheim. There I show you a beautiful project, which is Wheeled and Downland Museum in Great Britain. 20 years ago it was erected. This structure is very unique and beautiful, and there you can see the building process, erection, which is the most difficult part by building Gridshells. And there is the image of realized structure from the interior. You can see there is much light, and the structural wooden timber structure is really beautiful. When imagining about the future of Gridshells, I'm personally pushing for their promotion and development, and I believe that they will find their place and application. The biggest problem with Gridshell structure is the difficult implementation process, which still needs to be optimized in order to be more efficient. To understand and to be able to develop or to build the Gridshells, we made some student workshops at the university, Czech Technical University in Prague. And this is the result of our very first workshop. This structure was just a shape demonstration, and it started all the structure, every structure I create. I do start with physical models. There I used paper and plastic, so several types of material to reach the shape of the structure. At the end, we developed a chain suspended model in our studio under supervision of Jürgen Hennicke, who came to Prague to support us by the student workshop. We started with the flat grid in the front of the main entrance of Faculty of Civil Engineering. Afterwards, we wanted to cover an old basin in front of the main entrance, but this very first workshop wasn't successful because we didn't have much. We weren't experienced with building such a structure, so there were many troubles and problems, and we just weren't able to erect the structure. So we came then again in summer. It was 2015, and we tried to build this structure again on green on the grass. There is a erection process. I did build it with students and with my friends. During the process, it's necessary to leak the water on the structure, because then the timber elements are bending much better than when they are dry. So this is finalization of the building, of the structure. As you can see, and there is the completed structure, which has stood about 2 months, and after 2 months it was again dismantled. So this is the final picture of the structure. Another project we were involved in with Radek Podorský was a low-cost theater for mentally handicapped people in Neratov in Czech Republic. The goal was to design a like low-cost structure, which would be possible or which would function during 2 weeks during the theater. We again started with physical model. So this is the interior view to the physical model. And then we started with the grid, orthogonal grid, flat one, and erected. So the crane helped us to erect the shell. Afterwards, we did erect the shell. We fixed it, and the crane took it and put it on another place. The blocks of dry grass were used as walls, and on these prepared walls we again used crane to put the cap on the top. So this is the final realization. So you can see the physical model in compared to the finalized structure. Another project which we were involved in was Matrix Pavilion in Czech Republic again. Starting with physical model, very simple one, from the reinforced walnut. Then we made another physical model in the scale 1:5 on the grass, again in the front of main entrance of Czech Technical University. This is plastic pipes for electricity. Afterwards, I just tried, it was a part of my PhD research, to cover Gridshells by membranes. So we covered by membrane and supported by tennis balls, half-cutted tennis balls in the cross sections. And children did like it. Then we made some testing. So we bent the lattices to have some to touch them and be able to see how it works. This is the ground where the Gridshell was built, and my colleague with who I did test the shell. So there is some simple testing, very simple one. Then we made anchoring with the screws, with 2 meters steel earth screws. There were used 22. On these screws we made the edge, again made of the lattice, which was cross section 3 by 5 centimeters. All the structure. In general, we did use about 3 cubic meters of the lattices, which is not much, and it's we can say it's quite cheap, but the erection process, it's it's not simple. So this is the starting grid before erection. Afterwards, we again used the crane and we erected the shell. So there you can see the building process, erection process. The erection took about 3 months in 5 people, 4 up to 5 people, my friends, which was quite nice to collaborate with them. So we were successful, but still there got many troubles, and we got many experiences from this structure. There is the anchoring to the edge and the structure finalized. The structure was reinforced by steel cable net, which fixed the grid. And this is the final prototype in 1:1, erected in 2016. After 4 years, it was still in good condition. There we go, the comparison of the physical model with the finalized structure. There's some detailing. We used RGB lights to lighten the structure in the evening. There again, a finalized structure. And the opening was made by Dominik Duka, who is the Czech cardinal, and there was a ceremony, beautiful ceremony, at the beginning of the pavilion functionality. Here you can see we used a membrane. There is 45 square meters membrane, which is able to project the shadow of the lattice they are on the top. So even if you look at from the down underneath, you can still see the structure above. And this is the finalized structure again, just from another view. Another project was Wooden Trade Fair Pavilion in 2017, and it was for the Matrix company. We started again with the flat surface, and afterwards we erected in the final shape. The base of the grid is the wall. So it's suspended from underneath by the wall and by wooden elements. There we go, another project which I made with Lukáš Kurila and Tereza Žeková. It's just a prototype which wasn't built, unfortunately. This is our studio, and we just made another prototype. The point was to use ETFE foil to implement on the Gridshells structure and to see how it works. This mock-up is 4 by 4 meters, and normally the pressure allows in the middle to have 20% the height in the middle is in the pillow, in the cushion, ETFE cushion, is 20% of the span. So here by 4 meters is 80 centimeters in the middle. So we did build such a shell, such a mock-up. Here you can see the double curved surface, synclastic curved surface. We did cover afterwards by ETFE and anchored on the edge by aluminium profiles, normally used for one layer ETFE. There we can some detailing of tensioning the ETFE foil. And this is the final product. It was successfully, I again used for my PhD, and in the future I would like to use it again on the Gridshell. There you can see from underneath. So that was about the Gridshells, about our research, to be able to follow Fryoto steps and to be able to make some progress in the structures. We made these realizations, and when imagining about the future of Gridshells, I'm personally pushing for their promotion, and I believe that they will find a place in its application. One possible solution for greater expansion of the use of Gridshells is to create some simple element which would a smarter person be able to build himself. I'm currently working on such a prototype with the support of Matrix company, which is a Czech wooden production company. Unfortunately, I'm not allowed to share the result now, but I assume that I will be able to present by or during the next conference. At the end, I would like to share Shigeru Ban citat. Gridshell structures are one of many different interesting structural systems. If it happens that the Gridshell structure is suitable for the project, then I will use it, but if not, I will design another suitable system. The architect should not concentrate on one construction type and should always consider all possibilities. Without a perfect understanding of the design principles, we can particularly not design a building. So that's exactly what I think as well. And Gridshells are not for every building, but I hope they find their place in architecture in the future. Thank you for your attention.
All right. Thanks to Aleš Vaněk for his presentation. And next there will be presenting Šimon Prokop, who is cooperating with Lukáš Kurila. They're both from the Faculty of Architecture of Czech Technical University in Prague, and they will present about the generating design. So enjoy the presentation.
Hello everybody, my name is Šimon Prokop. I'm working with Lukáš Kurila, he's my tutor, and I would like to show you something about simulation-based parametric models of lightweight structures. It's a topic we came across while discussing design of these shapes, because it can get quite tricky when you don't have the tangible experience with building a Gridshell or something like that. And in order to make those structures work properly, you really need to get the shape exactly like it should be. And I think it's quite amazing that the tools we have today available are so powerful that they can teach us or give us this experience with these structures, and we can learn how those structures work, how they behave, and we don't have to cut any pieces of wood for that. And then when we go to design, we are quite confident that these things will work in a certain way. So I'm just going to show you these things in a design environment which is called Grasshopper. It's a Rhinoceros plugin which is meant to do parametric modeling. So we're going to be exploring some scripts here in the canvas, and we're going to see the result of that script here in 3D view. So I would like to start with this catenary curve thing. Thank you, Aleš, for this nice image of hanging chains, and also thank you for inviting me to talk here at this cool conference. I believe that everybody knows this catenary curve, but yeah, there's a mathematical equation for that. It's a cosinus hyperbolic of a t over a. Of course, we might know this curve more from real world whenever we have a chain or something with little pieces connected and it hangs in the gravitational pull of our of the Earth. It usually forms one type of this shape, the catenary curve. So let's jump into Grasshopper and let's see how we can model such a thing. So example number 1, a catenary curve. So I'm using this plugin called Kangaroo, and I'm just going to quickly explain what can you see here in this short script. So we have 2 points to start with. There's a line in between them, and we take that line and divide it into many points. It can be as many as we want. As many points, the more points you have, the more detailed the simulation is. And then we have to create these little segments. So we had points and we connect them with a line, and there's like many lines here. So these 2 points are connected with a small line, and these 2 points are connected with another line, and these 2 again are connected with a line, and so forth. That means we have something like a chain, right? It's many pieces connected together, and that's something we call a spring. So in here you can see that this goal object is named goal.spring. That means it's something which can extend and it can stretch and it can get shorter or longer, and that's something which allows us to do this, find this equilibrium state where every single one is stretching just enough to accommodate for the other forces in the system. As I'm talking about other forces, as we have all those points, we can apply some vector. Since we are interested in gravitational pull and hanging chain, I'm pointing all the vectors downwards. That means there's a force acting on every single point here. That's another goal object for our solver. And the third thing, very important, if I kept it running without these anchor points on the edges, the whole simulation would just drop down and everything would disappear. So I need to anchor it somehow, and that's another type of data here, goal.anchor. So with all these things being set, I can just go back to normal pink preview and let's run the simulation. So I just double click here, and here we go. We have this nice curve dropping down like this. Obviously you can see that it's a catenary curve, and if I restart the simulation, you can see that it bounces back and forth until it comes to as I said, the equilibrium state. Then actually no more iterations are needed, and this little message that the whole simulation converged to a stable state is displayed, and it's usually something around 2700. Like for this case, it took like 2760 iterations. The funny thing is, since this is a tension only concept, right? There are only little springs being tensioned. They are enlarged, like they're getting longer. If I switch the gravitation to the other side, this is a situation where such an object would be compression only, right? Because now it's not tension, it's compression. So quite simple, quite simple script with just 3 elements: the springs, unitary forces, and then anchoring on the edges can give us already some kind of idea about compression and tension only structures. Okay, cool. So that's a catenary curve. Then I'm going to show you this image, and I'm again going to assume that you know that Sagrada Familia had this cool model done by Antonio Gaudí, where many ropes were hanged from the ceiling and many sand bags were put on these ropes to actually simulate the shapes of vaults. And that's exactly what I was talking about. If it's hanging down, it's tension only, but if we switch the direction of gravity, it's compression only. So it's great for creating shapes of vaults. And let's check it out in 2D. Let's see a vault being formed using this script. So I'm just gonna go here, and again let's explain what do we see here. This time it's not a single line, it's a grid of points and lines, and this time we're gonna again do the same thing. Actually, we're gonna apply some vector force to everything. We're gonna take the lines in one direction, the other direction, make the little segments, right, interconnect everything in here. And the last thing we need is the 4 corner points. That's still the same thing as we had before. The only thing I added now is in here, and that's whenever I generate these springs, these little lines, I'm actually gonna ask the simulation to try to stretch, try to make every single line over here smaller a little bit. It's just 80%, but we're gonna see that this behavior is something we already seen somewhere before. So I'm going to turn on my preview, and let's just forget about these diagonals. I'm gonna talk about them in a moment. And if I make this simulation run, you can see that everything is trying to stretch. I can exaggerate this a little bit. We can see that we have something which to me resembles a membrane. If you look from top, we can see these nice shapes, and it's just a membrane. But then we can apply the gravitation. So remember, we had the points, and on these points we have some vectors, right? And that means we can, when those vectors are bigger, we can try to make a vault out of this. So if I apply this, when this is 0, it's just a membrane. But when I apply some gravitation to it, we can actually get back with the stretching, and we can see a nice catenary vault. And this shape is exactly like we've seen before. Sorry, go back to full screen. And that's quite okay. We have catenaries in this direction, even in the other direction. And the funny thing about this simulation here is I can try to get these corners closer to each other and see what happens with the structure. And I can play with this and can see what happens when I get them too close. It's just a piece of cloth, and it gets almost like that. And I can just go back and see how that structure behaves. There's one more thing I wanted to show here, and that's this this opportunity to interact with it. So when I apply some force to it, I can, you know, just take my mouse here and drag a piece of that construction and see how would it react to some external forces. And since it's very interactive like this, I can really see you know, what I'm designing before I start cutting some wood or, you know, some other structures. And again, it's still the same for the membrane. So if I just, you know, drop the gravitation like it is, and I can, you know, start dragging some points and see how would a really heavy membrane look like. I can start stretching the membrane and see what would happen if this was a shape I was going to model. So it's very playful, and I can see what would happen if you know, the constraints for this construction were different. Okay, cool. So we have this amazing tool, just a few goal objects for the simulation, and we can model nice walls, and we can model nice membranes, and it looks quite powerful, right? So I'm just gonna hide this and get back to my presentation, and I'm gonna ask a question here. Can we use the same method for the grid shell? Because it, like, to some people it might look like it's a, you know, it's a wall kind of thing. It's made from little pieces. It might be the same, right? So when we talk about grid shell, it's usually some spatially, usually double curved framework of rods. It has some joints, right? And usually we construct these things lying on a floor, and by pre-stressing the constraints or the anchor points, like, you know, usually applying some cable and pushing the supports closer together, we get this nice shape, which is usually a dome-like thing. So let's use the same approach here, right? So again, a grid shell is usually consisting of two systems, like one going in one direction, the other one going in the other direction. It can form different shapes, so I'm going to keep it to the grid so we can compare it to the previous thing we had. So again, let's jump back to our scripting environment. I'm going to start with a simple grid. I mean, not grid, I mean grid shell rod. So let's turn on the preview. It's just a line again. It's going to be very similar to what we saw in the beginning. Again, we have 2 points, right? Then there's a line, and we can divide that line into many points again. But this time we are just going to create a polyline. It is segmented, but it's one object only. It's a linear curve with many segments, and we're gonna use a different goal for this. It's actually a spring, but this time it's named rod, and it has this axial strength and bend strength. That means that as you have the polyline with many points, in every single point in there, there can be some kind of bending, and there's a lot of force in there. And this time there's going to be a little difference, that we have a lot of points, right? And the vector is actually going to be only on one of them. Like we can imagine we have a crane and we are lifting up this structure over here. This is how it's usually constructed. So we're just lifting it up at one point only. And you know, the rest is the same. We have these 2 points as as anchor points, and the last thing we need is actually something to pre-stress the bending polyline. So we're gonna create just a single line out of these 2 points, and you know, this line can then, using the slider, it can shrink, and that's gonna give us more bending in the structure. So I'm gonna start with number 0 in there, just a little bit of push from here, and let's see how does this work. So we have this blue line, and I'm gonna start the simulation. You can see that it starts going up slightly. it's bending, but there's not much room because we are actually it's getting longer, so we are putting some stress in there. But once I start shortening the bottom line, we can see some cool shape emerge. Again, it's just one shape like this. It's 2D, but we can see that this might be a good shape for a grid shell. So basically, let's look at this situation. So, now we're in 2D, and what happens when we put, many more next to each other and we connect them? So this is a simple one rod, and let's have a look at the grid shell as a 2D structure. So again, I'm gonna quickly explain what are we looking at. This script over here, again, we're starting with a grid. Of course, we can change the size of it, we can change the amount of things in here for the sake of this streaming, or I mean for the sake of recording, I'm just gonna keep it to simple 12 times 12, but we can go crazy with this. We're gonna pick a point to support all these things. This time it's gonna be a point in the middle. Let's see, and we're gonna apply some force to it. That's similar to what we had before. Then we need to do the same thing with the lines. So before we had one line as a polyline consisting out of many points. So in one direction, another direction, and these are going to be the rods. So again, it's a spring, but this one can bend. And the last thing we need is anchor points at the edges, of course, and then we're gonna need some pre-stressors. These are the cables which are going to be used to put the anchor points closer to each other to introduce more bending into the whole structure as I move this slide over here to less than 1. So I guess it's quite similar to the situation before. Let's go to the normal preview here like this, and let's make it run. So I'm gonna start the simulation here. By default, we could see that there's a little bit of bending, and since all these beams or rods, I mean, they are bending as well, there's the one point for lifting up is just enough. It's okay. And this looks almost similar to the previous example, but when we look from the top, it's still like kind of squarish. And the funny things start to happen when we start to use the pre-stressors. So I'm just gonna get this nice view, and I'm gonna slowly get the anchors closer to each other. And since this time we have bending in the system, from the top view it looks totally differently than the previous tension only or compression only structure, and we have these nice parts where there's a lot of bending, and some parts where the bending is not so hard. And the funny thing about this is when I get back to the initial position, and I'm gonna pick a different point for lifting it up. So I'm just gonna lift it up maybe from this point. I'm gonna apply this simulation again. You can see that initially it looks like this. It's maybe not gonna be symmetrical, but when I get back to lowering this number, we're gonna see some funny thing emerge, and gradually we'll get to the total is the same shape, right? So from the top it looks like this, and like despite a little bit of asymmetricity, because of course we're pulling it over here, it seems like we have the same shape. So the grid shell is quite resistant to other things. This is the shape for this kind of floor plan, right? So this is quite nice, and now it's time to ask a question. What's the difference actually? So I'm gonna go back, and we have Gridshells on this side, and we have these compression only things. We can think of membranes as well if they were hanging down. So is it just a catenary curve or not? Well, since you cannot answer me right now, I'm gonna be I'm gonna have to I'm gonna have to go back to my scripting environment and convince you that it's not the same thing. So I'm just gonna restart this, and I'm gonna go back over here and restart this and make it visible as well. So okay, maybe we should have the same size. So I'm gonna use this slider to say that it's 500 exactly. Restart this, and this is gonna be 500 exactly. So we have the same grid now, and let's run this one. And let's run the other one as well. So you can see that the shapes are totally different, even if we look from the top view. The pink one is the tensile only, or if it goes up, it's a compression only. We can see that there's a it's concave looking at it from the top view. And there's one more thing to make it matching. I can try to stretch the anchor points closer to each other over here, and we can see that both constructions react to this action in a very different way, right? So I can play with it a little bit, try to stretch it together, and this is the difference, right? So it's not just catenary curve, it's a whole different behavior. And I believe this is the strong thing about this tool, because we can run around and touch it, play with it, see what does it do when we apply some other forces to it, and this is building our intuition and experience, and that's, I believe, very interesting. Okay, so that's it, and I have one more bonus example, because so far we've been talking about tension only or compression only structures, and also bending active structures when there's moment in the structure, and this tool is actually enabling us to work with both tension and compression together. And a nice example of this would be the tensegrity structure. So we can see that there are some stiff rods which don't bend at all, and they are connected by cables which are working with the tension. And of course the rods are being compressed, right? And they're very good at it, so they don't compress that much. So let's jump back again, and let's see this another example where we are using both types of both types of action in our structure. I'm just going to enable this. We can start with this very simple example. We have 3 rods for the compression, and then we have always 3 cables coming from each end of each one, and it's in this cyclic manner, and this goes up and this goes up and this goes up as well. So this is a very simple setup. We can make it run by just double clicking over here, and you can see that the cables start pulling and the rods are resisting the stress, I mean the compression, and that's it. We can have this nice first part of the tower or something like that, and it's still reactive. So I can touch this point and see what happens if I flick this into space, and it's still reacting to my actually questions. I'm just asking, hey, little construction, what would you do if I pushed you over here? and this is quite stable. It's just a triangle, so it might be very useful for something which needs to withstand a lot. But I can get experimental. I can say, hey, why 3? I want 5, and I want it higher. And as soon as I restart my preview, so that we see what we actually set up here, I can make it larger or smaller. I can change the radius. It's still parametric. So let's see how this will work. You can see there's more action here if it's 5, because this one is not connected to this one, so maybe we're breaking some rules here. But this is building my intuition. I can still play with this thing. I can interact with it, and I can learn how such a structure could work. So basically, to sum up, we can model all sorts of structures which are using compression only or tension only, using springs. We can simulate as well bending active structures, something like a Gridshell, using springs which can bend on a polyline, and we can do all sorts of combinations of tension and compression as well. As an example, we've chosen the tensegrity structure. So here are some links which might be helpful, because you can download a 90-day evaluation version of this. For students, there are always some kind of discounts, and it's quite awesome. And you can start building your own simulations and learn how these structures work, and get your intuition in here. And I guess that's amazing. So I hope there's going to be some interesting questions on the break. Here are our contact info. We are from the Faculty of Architecture, and I look forward to hear what you want to say about these things. So thank you for your attention.
Many thanks to Šimon and Lukáš for joining the conference with the presentation, which for me personally was really beneficial. So thank you very much again. Because of time delay and no questions in the chat, we can skip the break and discussion. If you ask questions in chat now or afterwards, we can discuss them after second section. Now let me introduce my colleague, Professor Miloš Kopřiva, who is founder of our studio of membrane architecture and very important person in the Czech Republic who is promoting lightweight structures.
Dear friends of lightweight architecture, welcome to my lecture on the topic consistency between the use of membrane materials and the function of the building. I have chosen the topic of my lecture because I have been teaching students at our faculty to use membrane structures in their projects in about 8 years. I have often encountered a misunderstanding for the properties of these materials in relation to the nature and typology of the operation of the building to which a particular membrane technology is to be applied. The second reason is the decision of the pedagogical board of our faculty that membrane structures don't represent such an important segment of architecture that teaching about them can be a supported part of the schedule. So let me introduce examples in which membrane structures have become what not only solves not only the visual concept, but where they help as part of certain archetypes in general. There are applications of membrane structures of small as well as larger scale. In the lecture, I deal with a significant range of application of membrane structures. I don't mention the authors of the buildings. The reason is the time limitation and also the fact that the aim is not to comment architecture, but rather to monitor the frequency of similar applications. In public spaces, membrane structures of a significant extent are used for shading and roofing. A suspended membrane inside the public space, delimited by the administrative building at La Défense in Paris, completes the surroundings of the entrance area. Structures with the membrane are often rectangular. Courtyard of the town hall in Vienna, square in the Medina. They react to changes in conditions by moving their elements. It can be said that without the use of membrane structures, the variable architecture of the covering functions of the public space might not even have arisen. On the residential buildings, rather small additional structures with membranes are used, mostly shading or also roofing of the car parks. The buildings of hotels and temporary accommodation use membrane structures of a significant extent more. Here they are usually suitable for covering atriums of larger size, small membranes then for shading and phasing and protection of the entrance. Membrane structures are most often used in civil engineering. Office buildings use a significant extent to cover atriums or courtyards, smaller ones to cover facades. Examples from Prague can be shading elements of the facades of the office building in Smíchov, or the foil roofing of the atrium space on the office buildings in Karlín. Highlighting the entrance to the administrative complex of Free Europe building is an example of traditional concept. I consider it less suitable to use foils in parallel facade in front of the glazed areas on the Czech Technical University rector's office building of Cirk building in Davice. The view from such offices through foil is not comparable for employees to the classic use of glass. The manufacturers of film claim that it's possible to replace classic glass. Certainly yes, especially where the weight of structures is saved, but this example proves that this is not always the case. Single-layer roofing of outdoors restaurants is a commonly used technology in gastronomy. Some exotic destinations use membrane materials for facade elements, such as the holiday resort of Vela in the Maldives. Steel nets and multi-layer pneumatic structures made of foil are used in zoo cages. An example from the Czech zoo shows combination of glasses and the net of aviaries. The traditional roofing of the botanical garden is still the iconic Eden in Cornwall, because the ETFE film transmits the UV components of sunlight. Plants can grow naturally even indoors. Similar for foil materials can be designed in swimming pools and halls of water parks. The store represented by shopping centers use membrane structures for roofing, both fixed and rectangular. Here is present an rectangular roofing in Athens. Most often, various membrane structures of a significant extent are found in cultural, sports, and transport structures. Outdoor auditoriums and stages of cultural buildings often covered single-layer types of textile membranes, and circus marquals are traditional. Mostly these buildings are seasonal. Here I would like to give an example of my collaboration in the roofing of a replica of the Globe wooden theater in Kuwait City with my recently deceased colleague, architect Tomáš Kulík. The installation of the theater into the atrium of the existing building was to be covered with 2 textile membranes. Unfortunately, the implementation has not taken place. Finally, we most often encounter membrane structures in sport facilities and also in traffic structures. Stadium grandstands significantly saved the weight on unloaded steel structures when the filling fields are made of membrane surface. This will also be made possible by additional roofing of historical grandstands in large stadiums. The entire grandstands of the Olympic Stadium in Berlin were thus roofed for the 2006 FIFA World Cup. The steel construction is inserted between 2 membranes. Temporary roofing of outdoor sports grounds is now provided by industrially produced overpressure halls. Thanks to structure with ETFE foil fillings, aquaparks can have natural greenery in the interior. The roofing of transport terminals, railway station platforms, and other non-temperate transport structures are usually covered with single-layer textile membranes. However, there are also examples of very sophisticated types of structure inside ETFE overpressure cushions. The bus station in Aarau, near Zurich, has its platforms covered with this type of structure. Reconstruction of the large stadium halls can be made easier by replacing the glass with foil fillings. Such structure was used, for example, in Berlin. On the tower of the airport in Schwechat near Vienna, the shape and volume of the airport tower were unified by a cover made of horizontal stripes of membrane, on which motifs represented tourist terms and projected. we encounter a significant range of use of membrane structures in exhibition. In particular, the Expo World exhibition made extensive use of membrane constructions. Pneumatic shut-off became a symbol of the World exhibition at Expo 1970 in Osaka. The Fuji pavilion expanded the exhibition hall with cylinders with a diameter of 4 meters. The wrapping of buildings with membrane elements becomes an independent architecture discipline. This will allow you to work with the design of parametric models. The free form is represented by 2 examples: Leicester Racket Hall and smart water cube facade in Beijing. Working with a free form requires finding a relationship between packaging and internal operations. Therefore, halls with large span structures are more suitable for shaping than story layouts. At the end of my lecture, I would like to express my conviction that the field of membrane construction will be fully taught in the whole spectrum of the above-mentioned possibilities in the Czech Technical University architectural workplace. Thanks for your attention.
Many thanks to Professor Miloš Kopřiva, my colleague, for his presentation, which did cover the topic of usage of membrane materials. Now let me introduce next presenter. Now there will be Soňa Ballóková from the company Search Ferrari, and she will present about flexible composite materials in architecture.
Welcome to my presentation about flexible composite materials for lightweight and durable solutions. My name is Soňa Ballóková and I work at Search Ferrari. As a country manager, I am responsible for Czech Republic, Slovakia and Hungary. In 1973, Mr. Search Ferrari founded his company. 1 year later, he invented Precontran technology as an innovative coating process. His 2 sons, Sebastian and Romain, continued to run the family business. The company grew through the acquisitions of Batilite technology, the company Forbo in Switzerland, then Italian company Plastitex, and the last acquisition is German company Versailles, well known on tensile architecture market. Search Ferrari Group is now present in all 5 continents and in more than 30 countries as a technological leader in flexible composite membranes. Our 4 strategic markets are tensile architecture, solar protection, modular structures, furniture and yachting. Let's focus on tensile architecture to inspire you by the projects done with our flexible composite materials. The lightness of our materials opens up new construction possibilities. Architects and designers are offered new possibilities, enabling the creation of daring shapes and volumes while using less raw material and less energy. Search Ferrari provides solutions for open and closed buildings. The lightweight and flexibility of composite membranes offer freedom of shapes in origin design. Our composite materials allow the transmission of natural light to ensure a pleasant atmosphere. Our durable products keep their characteristics for a long time. Be inspired by the lightweight membrane covering the tribune of Interlagos Formula 1 racing ground in Brazil. The tensile shading on Interlagos Formula One racing ground uses properties and durability of Search Ferrari product Flexlite Extreme Take 30 Type 3. The membrane structure is visible during races, as you can see on the small picture under the black arrow. Tension structures are ideal for covering open areas, such as open-air sports grounds, play areas, or pedestrian walkway. They are also suitable for protecting goods, for example, covered car parks or carports. The picture shows the cruise line pier in Belize from above. It looks like a tip for your next holiday. Maybe 2022 it will be possible. The shading structure with Search Ferrari product Flexlite Advance 1002 S2 protects people on the pier. One project from Bratislava, Slovakia to inspire you. The light structure as a windbreak to protect people against strong wind because the building complex Panorama City is placed close to the Danube riverside. The architect Mr. Dolejší used Search Ferrari product Flexlite Advance 1202 S2 to create a dynamic shape. You can see the illuminated membranes at night on the small picture on the right side. Tensioned roofs are suitable for large span roofs, allowing the transmission of natural light and offer comfort by protecting against bad weather and the heat of the sun. Flexible membranes enable the creation of roofs or entire envelopes of closed buildings to optimize the transmission of natural light into atriums, shopping malls, sport halls or arenas, airport terminals and stations. The architects from Populous, UK, designed the tensile membrane roof for the football stadium in Rostov, which was built for the World Cup in Russia in 2018. The constructor Tensafor membrane used composite material Flexlite Extreme Take 30 Type 4. I am very proud to present you this beautiful project Ashram Meditation Center in India, the world's largest meditation hall and 8 satellite structures. The ashram is made with our Flexlite Extreme Take 30 Type 3 that combines high durability, aesthetic and excellent natural light transmission qualities. Our Alphalia SW as acoustic inner liner was used as well for its amazing acoustic performance. Flexible membranes allow the implementation of double skin thermal isolation solutions. As is the case with the Athletic Stadium Miramar, metropole in the south of France, the architect used Flexlite Extreme Take 30 Type 2 and Flexlite Lux 402 highly translucent product for a double roof. Flexlite Extreme Take 30 Type 2 is used for the textile facade, which you can see on the small picture. I would like to present you the iconic shape of the Exhibition Center Shanghai in China. The multi-purpose hall is a pioneering project and is an example of the innovative architecture using flexible composite material Flexlite Advance 1202 S2 for cladding, which reflects the modern context. The special metallic blue color brings dynamic to the new urban center, as well as an epicenter in the future development of Shenzhen. The natural light transmitted through flexible membranes ensures pleasant lighting for optimal user comfort. To provide more daylight, Search Ferrari offers flat light products like 1002 highly translucent, with a visible light transmission TV 15%. Such Ferrari provides materials with different visible light transmission to meet all requirements for visual comfort. For example, TV of Flexlight Advance 1002S2 is 5%. For highly translucent 1002 HD is TV 15%. Flexlight Lux 402 HD for inner membrane has TV value 37%. Serge Ferrari developed a unique transparent material for membrane architecture, Flexlight ST-FE with TV 50%. The choice of the more translucent material Flexlight Advance 1002 HD in the center of the tennis club is giving a spine effect to the roof and contributes to the architectural statement, as you can see on the right picture. Multimedia material roof of Westlake High School in New Zealand used PVC-coated material Flexlight Advance 1002S2 and ETFE single skin, the picture on the left. Frequentrend technology, protected by a worldwide patent, enables the production of flexible composite materials with exceptional dimensional properties. The technology consists in applying a coating under biaxial tension along both the warp and the weft during the whole manufacturing cycle. The materials using Frequentrend technology thus acquire unique properties in terms of resistance, dimensional stability, and lightweight, eliminating deformation due to load, offering a longer lifetime and enable easy cleaning. Serge Ferrari has been creating a multi-material offer for tensile architecture depending on the requirements. Tensile shading or enclosed tensile building, as well as facade, double or single skin. Serge Ferrari's composite materials offer high added value for aesthetic design, thermal, visual and acoustic comfort, as well as for durability and sustainability. Please use this overview to find the best solution for your project to match all assignments. Serge Ferrari collection consists of Flexlight Extreme Range, which consists of very high performance membranes, thanks to the cross-link technology. The mechanical longevity is directly linked to the quality and thickness of the coating, which protects the yarn from UV. Flexlight Extreme Take 30 longevity is served by a 30 years coating formula that is highly resistant and a thicker coating protection at the top of the flat micro cables thanks to Frequentrend technology. This range is ideal for complex projects involving translucent roofs. Flexlight Lux products provide high visible light transmission up to 50%. Flexlight Advanced range with PDFE varnish combines long life, consistent color per translucency, and easy maintenance. These composite membranes enable the creation of shade structures in a wide variety of applications. This is an example of characteristics presented in datasheets which are available on our webpage. Please don't hesitate to contact me in case of any questions now or in the future. Serge Ferrari's facade solutions are a source of inspiration for all bioclimatic facades, offices, mixed-use buildings, shopping malls, residential projects, public buildings, hospitals, schools, or car parks. Frontside micro-perforated composite membranes can be used along with other materials or alone as a main cladding. Our facade range offers unique advantages: aesthetic, 3D volumes, curves, lightening effects, printed, durability and resistance to all weather conditions and UV. Our solutions are lighter than other common materials, offer thermal comfort and energy savings, preserve off outside views while limiting dazzle, easy installation for new building and renovation projects too. Enjoy the dynamic facade of Costa Hotel in Turkey with frontside view 381 on the picture. One single color of frontside view 381 reflects light to cover the building with a changing metal skin, as you can see on the tensile facade of the restaurant in France. Single skin facade of the car park at Schuko headquarters in Germany is done with frontside safe P35. This special product is a non-compostable mesh for textile facades which meets the strictest requirements in terms of fire safety and obtains a flame retardancy certificate A2 according to the European norm. This tensile facade on this building filters heat and limits energy consumption. Printed mesh frontside view 381 provides personalized graphic and design identity to the car park at Rice University in Houston, USA. In the sun, the facade of this building presents an opaque metallic feel, and when night falls, under the LED lighting, the hidden building structure can be realized, as you can see on the picture of the Hotel Fischer in Austria. The next example of the double skin facade is printed mesh used for the library La Passerelle in La Tour de Pas in France. You can find the same printing on the ceiling inside the library. The printing company Point in Medlow, close to Brno, decided to renovate its production building. The new facade was designed by the company Architects, now a part of the company Karstahl. The mesh frontside view 381 is applied as a double skin facade to provide the significant thermal protection. There are the pictures before and after the renovation. The old building obtained a modern and industrial look thanks to the tensile facade. I proudly present you the iconic tensile facade of Tower Tower restaurant on the private island in Maldives, which was designed by architect Mr. Hirnschall and done by the company Contis Praha. The architecture of this restaurant sets it apart from all the other buildings on the island. It's modern and futuristic. All elements on the external perimeter are shaded in a light grey semi-transparent facade. Frontside view 381 preserves outward visibility with unique panoramic view while limited dazzle. One building complex with living facade. On the picture above, the facade mesh protects us from glare and ensures privacy during daylight. At night, the facade changes the building to the lighting spaceship. Textile facade is an attractive, durable and efficient solution for renovation, especially if there is not enough budget. This picture shows us the West Hill Medical Office building in US before the renovation. And here is the same building after the renovation. The change is stunning. Sport arena in Baku has seen better days. How to renovate this old sports gem with limited budget? The lightweight solution with textile facade has changed the old-fashioned stadium to the modern sport complex. Serge Ferrari's range for tensile facade consists of frontside view 381 with a wide color range, frontside print 371 for printing, and frontside safe P35 as non-combustible facade mesh for the strict fire safety requirements. Tensile facades can come in various forms and shapes like freeform, monolithic facade, framed or cladding facade. Tensioning system depends on architect's intention, design and technical options. There are some examples of the tensioning systems: aluminium frame, tension bar, cadder system, lacing system, springs, or tensile architecture. A well-known producer of tensioning facade system is a German company Facit, today a part of Schuko company. The Swiss company PTS is a specialist in textile and bioclimatic facade systems. Isermatic Systems is a French producer of systems for fabric tensioning. Thank you very much for your attention.
Now Karl Gruber is ready for next presentation, which is focused on the company CON, Belgian company CON, which is a producer of technical textiles.
Good morning, ladies and gentlemen. I am pleased to be able to introduce our company CON Industries to you at this Congress. The current circumstances force us to use electronic tools. Of course, I would have been happy to present myself on site. And now to our company. CON Industries is a shareholder company and is now again almost 100% owned by the CON family. The CON Group is divided into three large divisions. The largest division is CON Coating, followed by CON Apparel and CON Chemicals. CON Industries generated sales of 506 million euro in 2019, with almost 5,000 employees. 62% of sales are generated by CON Coating, 26% by CON Apparel, and 12% by CON Chemicals. Sion Coating is a fully integrated manufacturing company, produces yarns, raw materials, non-wovens, mesh fabrics, up to coated fabrics with various coating thermoplastics, mainly PVC and polyurethane. But we also deal with other coating materials such as silicone, PVC nitrile, alloy, and others. Sion Apparel produces professional protective clothing, from protective work clothing to sports and casual clothing. Most of the raw materials are produced in-house. Sion Chemicals supplies fine chemicals such as color pigments, master batches for the coatings, varnishes, etc., up to digital printing inks. The coating division produces in 7 factories in 7 different countries in Europe. As already mentioned, Sion Coating operates a fully integrated production line. In our spinning mill in Moucron, Belgium, 16,000 tons of high-tenacity polyester yarn in various titers are produced per year. Since the total capacity of 16,000 tons cannot be covered by our own requirements, yarns are sold for other applications. We operate 2 weaving mills at Moucron and Kerksken in Belgium with more than 250 looms. Not only high-strength polyester yarns are processed for our coatings, but also base fabrics are made from other raw materials for the external markets. In Liège, in Belgium, and Valstagna in Italy, we operate 6 needle punch lines with associated finishing lines. Our high-tenacity polyester yarns are sold for different applications, such as geotextiles, ropes, conveyor belts, and many more applications. The majority of the woven fabrics are processed in our coating plants. Raw fabrics are also supplied to other applications and markets, such as food, heavy and chemical industries. Among other things, we also produce very high quality fabrics for tea bags, such as the automotive industry. Products for a large number of applications are manufactured in the coating plants. The product range extends from transport to agriculture, camping, sports, advertising, industry, and much more to tensile architecture. We produce with 6 different coating technologies: direct and online coating in Belgium and France, transfer coating in Belgium and Portugal, melt or extrusion coating in Belgium as well, calendar coating in Moucron, and laminating in Germany and USA. Needle felts are manufactured for the following applications: filtration, automotive, and construction. A member of the Sion Group, Dimensions Polyant in Germany, produces high-quality silk clothes. Dimensions Polyant has a world market share of more than 40%. 90% of all important sailing races are equipped with products from Dimension Polyant. In the companies Cotex and Sanfrea Induction, Keda materials and pond liners are produced. The companies there are also able to operate with different cutting technologies. We also run a confectionery in Sanfrea. Sion Apparel produces with 2,300 employees in 13 factories in 10 countries around the world. Their own brand products are developed and designed in-house. A very large showroom can be viewed at the headquarters in Ardoye. Sion Apparel produces protective clothing for all areas and requirements. Forestry is a specific market. Special but safe and light clothing for good wearing comfort is required. Protective garments for the fire brigade, according to the standards of the individual countries around the world, are produced. Protection and bulletproof vests for use by the police and army. Inflatable life jackets and flotation suits for marine safety. Functional, comfortable and durable workwear for any working condition. Casual wear for fishing, hunting and leisure. Sion Chemicals produces with 158 employees in 3 factories in 2 countries. The main products are pigment pastes, lacquers, inks and much more. Sion Industries produces ISO compliant and REACH conform and massively increases the commitment to proactive, sustainable product development. Why do we deal with lightweight construction? What will the construction industry look like tomorrow? We should stop acting immortally and thinking that our resources are limited. We have to think about future generations and have to stop senselessly exploiting our ending raw material deposits. I do not want to go into any further problems resulting from this, such as climate change and many problems more. The world population will increase to 10 billion people by 2050, so by 7 billion in 100 years. How can we meet the building needs of 10 billion people? With the help of the graphic, you can see how gigantic the demand for raw materials is for some of the European countries in the construction sector. In addition, the CO2 emission of the construction industry are 40% of the total emissions. Every German consumes an average of 490 tons of building materials, approximately 50% for infrastructure and 50% for buildings. 4.4 birds per minute faces 1.8 dead. If the population grows as expected, then by 2050 we will need 2.6 times more than our existing building environment. In addition, we have to rethink climate, energy, and environmental aspects. Furthermore, we have to build energy and CO2 neutrally. Tensile textile constructions are one approach to solving these problems. Membrane constructions in lightweight construction that can withstand high loads and have long durability can be used in many areas with an attractive shape and design that is far removed from conventional constructions. Textile membranes only follow tensile forcing in their shaping. There is no decompression. Flexible air-supported constructions for quick assembly and dismantling. Very large air domes up to strength type 5 are now being built. Air domes for all possible applications. Here an aircraft hangar in Riyadh. Double membrane systems for swimming pools and sport fields. Textile facade generates a lot of improvements from building aesthetics to physical properties. the possibility of giving a building its own identity, reduction of environmental impacts through the second skin of the building. Additional technical lighting effects can create a completely different impression. With the facade mesh as the second building skin, you can control external influences such as temperature, solar, radiation, humidity, noise, light atmosphere, and wind accordingly. Facade mesh can be used in different colors, right up to metallic colors, for example, only used as a partial facade. The mesh can be digitally printed. Translucency, transparency can be adjusted accordingly. We have a large number of different reference projects available. Fluorscreen is a highly translucent fluoropolymer-coated glass fiber mesh. The fabric has a low wick finish and corresponds to a strength type 2. The light transmission is approximately 93%. The fabric can be HF welded directly. The fabric is ideal for projects that require high levels of light transmission. Fluorscreen can be welded directly to PVC-coated membranes or mesh fabrics. Many thanks for your attention. I must tell you, it's the first time that I have given a presentation this way. I therefore apologize for any shortcomings. However, I wish you a good day and a successful symposium.
Thanks to Karl Gruber for the detailed informations about the company CON and their products. Next in the schedule, there is Kibra Talak from Stuttgart company called Structure. Stuttgart is the city where Frei Otto has taught. He has their lift, and it's like a world's famous place of rising lightweight structures. So enjoy the presentation of Kibra Talak from the company Structure.
Hi, my name is Kibra Talak. I'm from Stuttgart, Germany, and I studied structural engineering at the University of Stuttgart and joined Structure 2 years ago. Today I want to give you an insight into my research work about PTFE fabrics and their strength behavior for changing loading speeds. Before I start, I would like to introduce our office and show a few pictures of what we do. Structure is an engineering office which was founded 2012, and today there are 3 partners. All 3 are holding their professorship. Michael Hermann is at the Technical University of Lübeck, Julian Lienhardt at the University of Kassel, and Alexander Michalski at the Technical University of Konstanz. This is our team with 8 structural engineers, 3 architects, and 4 working students. For a small overview of what we do, I chose projects which are different in their challenges. The first one is a hotel in Oberkochen, Germany. You see in the first picture the analysis model, in the second you see a rendering, and the third one shows the finished building. Second project is Arad Express, which is a timber membrane construction as a roof for a valley station of a ski lift in Austria. As a reference project for membrane facades, I chose the Adidas facade for a parking garage. The geometry is simple and complex at the same time. Where the geometry of single triangular steel frames covered with membrane are quite simple, the global geometry is very complex and was found with the help of parametric design. Last but not least, we are also doing research work, such as here shown case study about computational simulation allowing realistic assessment of all wind phenomena and response mechanisms of tall buildings. The projects on this slide have one thing in common. As you may see, all are examples for convertible membrane structures. And they have one more thing in common. The membrane which is used here is always PTFE fabric. For convertible structures, there are two materials which are used the most: PVC-coated polyester fabric and PTFE fabric. For cost reasons, polyester fabric is more often used. Unfortunately, the durability is limited due to its sensibility to UV light. PTFE fabric has a very high durability, is self-cleaning, and is very suitable for the use in convertible structures. Major reason why PTFE is not very often used is its costs. PTFE fabric costs about 10 times more than polyester fabric. So, we would like to see more projects where PTFE is used, and had this idea of research work where we wanted to show that this fabric material could be used more efficiently by learning more about its strength behavior. The background of this idea is that for membrane structures, wind load is always the decisive load case, which is a short time load. So loading with a high speed. And there is a lot of research work for different materials where a considerably higher strength was determined by material tests only with the use of higher testing speeds. So let's start. Here the main content of the next minutes is shown. I would like to start with a general introduction and continue with more specified basics as a preparation for the next chapters. Chapter 3 contains the numeric simulation of an umbrella with 53 meter span. Chapter 4 gives an intention for the material stiffness behavior under test conditions with varying testing speeds. The aim of those tests was to prove the assumption of a constant E module in the simulation, so to prove the quality of the results in Chapter 3. The main content is shown in Chapter 5, where you will see if we could prove higher tensile strengths. I will also show 2 videos of the tests here to give a feeling for the chosen testing speeds. Last chapter gives a conclusion and outlook. Membranes of convertible structures are changing from form and tension. Therefore, kink-resistant fibers are needed qualification. As I told at the beginning, the 2 most used fabrics are PVC-coated polyester fabric and PTFE fabric. One of those convertible membrane structures with high demands on durability is the membrane roof Kufstein in Austria, with a span of 50 meters, where PTFE fabric was used. Why PTFE? It has good mechanical properties, high UV resistance, is self-cleaning, high durability, high kink resistance, high comfort, and high light transmission. Why not PTFE? Very cost-intensive and water permeable. Last one is only half true, because there are PTFE fabrics with thin film of fluoropolymer without any influence on mechanical behavior, even with a water column of more than 2 meters. Such a material was used, for example, for the Kufstein project. Here's another project where the roof is sliding aside on rails, what we see on the right picture. It's a convertible membrane roof in Bug, Switzerland, and is about 50 meters long. Here we see an umbrella with a span of 53 meters, with PTFE membrane, which is also the reference project for the simulation in the next chapter. The aim of this work is an investigation of the material's performance and therewith to increase the efficient use. In view to the design, this means that we are talking about the characteristic value for tensile strength, which is here given with FTK according to the design concept of TensiNet Design Guide and JRC Science and Policy Report. The decisive load case for membrane design is gust wind. So we want to see which characteristic tensile strength we will determine for higher testing speed, which corresponds to a gust wind. Basics. PTFE, or polytetrafluoroethylene, is a partly crystalline polymer of carbon and fluorine with unbranched linear structure. It shows a very high heat and chemical resistance and the smallest coefficient of friction among all plastics. Another property is its pronounced tension creep behavior and anomaly regarding thermal expansion coefficient, especially at 19 degrees. Here, an overview of the mechanical behavior of fabrics is given in general. Fabrics are anisotropic, orthotropic, caused by the two thread lines orthogonal to each other. Nonlinear, because there is no compressive force, and there is the effect of constructional stretch. Fabrics are non-elastic, means that the deformation is not fully reversible. Numerical simulation of 53-meter umbrella. The simulation was necessary to figure out which loading speed would be realistic to choose for the test to emulate a gust wind effect in membrane. So we need strain rate, which represents the loading speed in material. Here I used results from wind tunnel tests for this 53-meter umbrella. There, a load per time step was given for each area on the membrane, which I could use for a time step integration and sophistic. This video is a sequence of deformation plots per time step. But here only the section is shown where we see the effect of gust wind at the end of the video. Sorry. We can see the effect of gust wind very clear in this force time graph, which is shown for one quad element. Out of the elongation time graph, we can determine the strain based on Hooke's law for 2D stress state. And finally, we can determine the strain rates by the integration of the elongation time curve, which further defines the testing speed of 500 mm per minute based on the length of the samples. So in this case, the effect of a gust wind corresponds to a loading speed of 500 mm per minute. A short intermediate step test for stiffness characteristic. I'm very thankful for the support of the Institute ITKE at the University of Stuttgart and the Institute 11 at the University of Duisburg-Essen. In Essen, I used the biaxial tensile testing machine to determine the E-module for changing testing speeds. The aim was to verify the correctness of the assumption for a constant E-module in the dynamic simulation. The results are showing a change by a factor of about 1.1 up to 1.3, which, referring to the E-module, is not much and means that the assumption for a constant E-module is still realistic even by changing loading speed. Test for determination of strain rate dependent tensile strengths. I made those tests at the testing laboratory of ITKE by using the Zwick testing machine. And for a precise measurement of strain, I use an extensometer, which is seen in figure 18. It wasn't easy to test PTFE fabric. Due to the very small coefficient of friction, the material slips easily out of the clamps. After a few tests, it became clear that special clamping systems are needed to ensure that the material won't move in the clamps. And this one is the first I used for the tests. But since I tested 4 different material thicknesses, this system didn't work for all cases. But what we see here are the clamping jaws and aluminium profile and one M12 bolt, which is fixing the membrane in the aluminium profile. Second clamping system is a little different. Here I didn't use the clamping jaws anymore, because sometimes the profile moved a little, which falsifies the testing results. Here, actually, we can say that the testing machine has been modified by using steel profiles, which are holding back the aluminum profile. The membrane is fixed by a M10 bolt and a pin. The last one I developed is clamping system number 3. The steel profiles are used again, but this time in combination with bolts, which are pressing 2 steel rolls against each other. Before using different clamping systems for different materials, a conformity check was done to show that all 3 systems are leading to same results for one material. This graph shows force elongation curves for same material but changing clamping systems, and we see that the results are very consistent. Here we see one unloaded sample and one sample which was loaded with a testing speed of 100 mm per minute, which is the testing speed according to standard EN 13934. The manufacturers are using this testing speed, so it was important to do the tests first with the same conditions as the manufacturers do. Only in this way we can evaluate the change in tensile strength between 100 and 500 mm per minute. This is one of the force elongation graphs for 100 mm per minute. The blue box shows the interesting area. The other half of the curve is always changing in dependence of the undefined tearing. The peak gives the most important value, which is the breaking load. The characteristic value is related to the population 5 percentile value obtained from the test results. Here we have a video for a testing speed of 100 mm per minute according to standard. We will see in this area the material will break. And here a video is given for a testing speed of 500 mm per minute, which was determined for a gust wind effect. Before I started with those tests, I was very unsure if we will see a clear increase of strength. But as we see here, the change is very clear. In this case, the maximum tensile strength for a loading speed of 500 mm per minute was increased by a factor of 1.2 related to the tensile strength according to standard. What we also see is that the curves are very uniform. This is a sign for a displacement-free clamping system and almost exactly same testing conditions. This is also shown by the small coefficient of variation, which is given in the table here with 0.01. This material shows an even higher increase of strength by a factor of 1.3. This one same. And also here we see an increase by 1.2. We saw test results with different PTFE fabric materials and 2 testing speeds. 100 mm per minute according to EN 13934, which was used as a base for the determination of the increase in strength, and 500 mm per minute as an effect of a gust wind. There was an increase of strength by a factor of up to 1.3 towards testing speed according to EN. 3 clamping systems were developed, particular for PTFE fabrics. In future investigations and examination of further structure types for comparison of strain rates would be interesting, especially to define the effect of curvature, pre-stress, and type of supports into the strain rates. Also, the increase of strength in areas with details and seam areas are interesting. Overall, a factor of 1.3 would mean that the membrane could be designed for a 30% higher tensile strength. And since the price is rising disproportionately for thicker membranes, Conversely, this means that by the use of thinner material, the price will be reduced even more. The advantageous properties could be used more often in future projects, which leads to high-quality structures with a long lifetime and smaller environmental impact. This brings me to the end of my presentation. Thank you very much for listening and enjoy the rest of your day.
So many thanks to Kibra Talak for her very specialized presentation on PTFE fabric. And this presentation ended up the second section of the conference. Now there are some questions addressed to Samuel Fournier from Vector Foiltech. I will read and answer the questions. First one. Hello, 35 years long-lasting of ETFE are for European climate? The answer is yes, 30 years in any climate. And the second question is the material suitable for to be used in Asian climate? Thank you. The answer is ETFE doesn't show any degradation from UV radiations, environmental agents. This is valid for both transparency and mechanically. Now we have time for lunch and coffee break, and we will meet. We'll be back again at 13:50 Prague time. So thank you for listening and meet you soon. Dear friends of lightweight structures, welcome back again to watching the international conference Architecture of Lightweight Structures, which is broadcasted from the studio of Membrane Architecture at the Department of Architecture, Faculty of Civil Engineering, Czech Technical University in Prague. The architect and designer Patrik Kotas will present first lecture in this section on the topic Pioneering Realizations of Lightweight Structures in the Czech Republic.
Hi, my name is Patrik Kotas. I am architect, designer, and in the same time a teacher at the Czech Technical University at the Department of Architecture of the Faculty of Civil Engineering. My greatest interest in the scale of architecture and design are buildings and spaces, public spaces with light structures, especially with membrane structures. Why? When I was a little child, I was very strongly influenced by books and ideas of Jules Verne, and also by others writers and creators preferring high-tech technologies at the end of 19th century, at the beginning of 20th century. So that's why my start of my architecture praxis was based on public spaces, on transportation buildings, on design of transportation means, and so on. It's clear that the greatest symbol of the era when textile membrane started, the great period of development of technical highest level, was this building, Burj Al Arab Hotel in Dubai. It's clear that this building influenced me as the image, symbol of lightness, of combination of steel structure and membrane design. The silhouette of this hotel was for me, when I saw him for the first time, the passion, the experience totally strong, and I feel that it's the way that I would like to follow. Another experience that influenced me as the living symbol of membrane architecture is Geneva port, and the great work of Renzo Piano. This roof cover in the space with the port, with the sea border, was the second more strong influence for my work. At the beginning of new millennium, I was invited as architect and designer on the project of new tram line in Prague, connecting south end of Prague in Hlubočepy with new residential quarter on the hill of Barandov. This new line has different character in contrary of existing Prague tram network, because this line has another character depending on the territory where the line is situated. The tram line has the character of a completely segregated high-speed rail body, or high speed. It's the scale of tram line, and please imagine that the speed represents 60-70 kilometers per hour, but it is not line situated on level of streets. It's line situated of totally separated space body, as I mentioned. One of these stations, which named Barandovo, has concept with two platforms, two lateral platforms covering by light steel structure, and the stairs and vertical connections are covered by membrane structure. At the beginning of a new millennium, it was first real project using textile structures for public space in the scale not only small entrance areas or something like this. It's really structure covering half part of this station, of the platform, of the stairs, as I said. This steel structure bring a new point of view as architecture, as membrane architecture here in Central Europe, in Czech Republic, could represent the architecture design for transportation buildings. Here you can see the combination of light steel structure of pedestrian bridge as the main symbol of the station, with the roof covering the stairs and other additional spaces. This project for me was great, bring me great force to use membrane structures for more larger projects in larger space here in this territory of Czech Republic or middle part of Europe. The second project that I would like to present you is the project of bus terminal in the city of Hradec Králové. Hradec Králové is the city with 100,000 inhabitants, situated in the eastern part of Bohemia, approximately 1,000 kilometers from Prague. And in history, bus terminal was situated on a square bordering with railway station. It seems to be logical that railway station and bus terminal are connecting in the same space, but it presented great urban problem. The space connecting railway station was created as the classic square, classic city square, not as the crossing point, or not as the transportation hub. That's why the city of Hradec Králové organized architecture and transportation engineering company how to develop the space of this square, which named Rieger Square, and how to found the solution reserving the connection between a railway and bus terminal, but replacing bus terminal outside of the classic city square. Me and two my colleagues, architect Jan Štípek and architect Jaromír Chmelík, we presented the competition concept based on replacing this old bus terminal from the space connected with railway station on other space situated approximately 300 meters from old historical building of railway station, and install on classical square pedestrian space with bus and trolleybuses stations of mass transport, city mass transport, but bus line, long haul bus line situated on another new place on the right side, as I mentioned, 300 meters of distance. And on the same space also the the terminal point of a whole network of city bus lines and trolleybuses lines. The result was totally refurbished space of the square. Now you can see how the Rieger Square was totally rebuilt from the space with bus platforms and crossing points, etc. Now it's really square with pedestrian space, with public water element, with trees and so on. And the historical facade of old railway station now is clear, it brings new feeling, new symbol of old railway station. Why? Because now the main facade is visible from the whole large visual axe of this space. That's the pedestrian zone with fountain. and the artificial lighting system of the square. And here, that's the concept of new bus terminal. It's based on two separate check-in halls. The left hall is reserved for mass city transport, that means for bus and trolleybus network. But the right side hall is reserved for long haul bus lines and also international bus line. It seems that two structures with the same shapes and two same system of suspended steel structure brings idea of wings. Yes, it is, because this project for competition was created during my journey to Geneva, and you can see how I was influenced by Renzo Piana project of Geneva port. This structure used membrane textile. It's original material from Ferrari company, as company able to offer a really professional system on great dimensions. The roof are suspended on area with 22,000 meters squares, and the dimension of one suspended wings are 20 meters of longitudinal dimension and 30 meters as the crossing dimension, as the elevation of one wing, if you can see the elevation view upstairs. The vertical steel trusses with a flat, which keep the diaphragms in a horizontal position via the system of rods significantly exceeded to the height of check-in halls. That's the basic concept, and here you can see how the great bus terminal with both check-in halls look during night or evenings. The lights, the design lighting system is part of architecture. It's not something additional. It's a really basic part of architecture. Structure design, space design, and lights are connected in the same concept. At the first part here you can see the mini round point crossing with suspended light element Another dominant element are two mini roundabouts which, due to the cramped environment, use the principle of rotational movement of vehicles in the entire area. Vehicles pass through the center of the intersection. We had to figure out how to do this so that the pole and the traction line connected to it would not stand in the middle of the junction, as is often the case of roundabouts with traction line. The resulting solution is a white steel bolt, politically speaking, a ring. This detail switches the entire suspended structure of the contact wire and at the same time illuminates the intersection from above in the middle of several circles of white paving blocks. In addition, it represents a distinctive architectural symbol that corresponds to the motif of circles at intersections of the bus terminal. I would like to believe that this use of this bolt is completely unique solution in Europe. The complex is also equipped with a special information system and a system of indirect lighting. The light of the lamps does not shine directly on the titles, but is reflected through elliptical discs with scattering surfaces attached to the supporting structure. Diffused light does not dazzle the passenger and in the same time provides as good lighting as direct light. The lighting and information system is largely made by LED technology. There are so-called lights trail in the paving of sidewalks and roadways, which are distinguished by color and complement the distinction between blue and red zones. The red zone is reserved for urban public transport and the blue for long-distance transport. Checking holes are divided in the same way. The intention of two-color composition was to allow passengers a quick orientation in this bus terminal. The checking holes are generally glazed, including saddle roofs. The glazing of the facade has a practical purpose, an easy overview of the dispatchers of the transport terminal, and overview of everything that is happening in the area of bus terminal. It is also made possible by the seat of the control room in a cosmic-looking sphere with smoky glass. It's also made possible by the seat of the control room in a cosmic-looking sphere with smoky glass, which is suspended by a rod of the height of second above ground floor and connected to it by a suspended reinforced concrete footbridge. From certain angles, when the footbridge in alignment, it looks as if the sphere can only be entered by descending to ground and launching an entrance staircase, like a spaceship. It's practically a steel structure with a diameter of 430 centimeters, on which spherical colored glass is glued in the transparent zone. The lower and upper poles of the sphere are provided with a laminate construction covered with a mirror varnish. The membrane character bring to the building in relation to surrounding new panorama, new silhouette. But of course, it also has a practical function to protect passenger from bad weather. There are different types of membranes. They differ in durability, resistance to ultraviolet sunlight and surface treatments. As I mentioned, the membrane used to cover both wings of terminal was supplied by a Ferrari company. So, it was my presentation of two projects bringing me new personal experience with membrane structures. For me and for my architectural studio, it was a very rich period, and I am very satisfied to be able to realize these two projects. Please will you excuse me my bad English, but I hope that the photo and some feeling of this architecture is able to bring you little bit good or better experience. Thank you very much for your attention, and I hope that membrane architecture will be our common love. Thank you very much. Goodbye.
Many thanks to Patrik Kotas for a nice presentation about his projects, which aroused public interest in the topic of lightweight structures in Czech Republic. For the next presentation, there is ready Lubomír Konečný from the company Kontis, who have realized most of the structures in the Czech Republic.
Hi, my name is Lubomír Konečný, and since 1995 I have been working for Kontis Praha, which has been dealing with textile architecture for 22 years. Our first realization of membrane structure took place in 1999. We were approached by architect Střítecký and his studio A8000 for a realization of permanent textile structure for the first time in the Czech Republic, Voříškův Dvůr shopping center. Since then, we have been successfully spreading awareness of textile architecture among the professional public in the Czech Republic. Among the important architects who have shown us confidence in the implementation of their projects are the already mentioned Studio A8000, Atelier ADR with architect Peter Kolář, who also uses our company for his foreigner realizations, such as the facade of the observation tower on one of the Maldive Islands. At the end, I would like to mention Patrik Kotas, who entrusted us in the implementation of transport construction using textile architecture, such as the Barrandov tram station in Prague. I will not mention the principles of building design in the textile architecture and the materials used, although this is an interesting topic. Colleagues have already introduced you with this topic at this conference. I would like to apprise you with some project implementing in the Czechia or Slovakia. I would like to dedicate most of it to newer trends in this discipline, namely textile facades. The first such project is a 3D textile facade on the new building of a support primary school in Banská Štiavnica. Realized area of the facade is more than 1000 square meters. Year of realization 2018. Used fabric is front side 381, clamped in anchor rails, PTS profile, aluminium 80 by 40 millimeters. The architect's requirement was that this textile 3D facade intensively reduce the transmission of heat and light into the interior of building, the glazed modern construction of the school facade. The front side 381 fabric used has a 28% solar permeability. In this way we managed to meet the architect's request. The 3D effects of the facade was problematic. The architects demanded the production of a facade without cuts that would spatially shape the 3D effects. We used the service of structure engineering Peter Feynman, who tested the materials and this attachment on a tearing machine so that we could achieve 3D shaping of the fabric by using its slight flexibility and at the same time preserving its stability. This solution was verified by test sample of a part of the facade installed at the construction site. The functionality and stability of the test specimen was the base of approving the proposed design of the 3D facade. The actual installation of the 3D facade took place in these phases: installation of all aluminum profiles on a supporting steel structure, stretching of fabric and attachment to aluminum profiles. We anchored the tarpaulin with a PVC pan into the groove of the profile and secured it with an aluminum securing T-strip. Already in this phase of October assembly there was a radical change in temperature condition in the building. The whole construction thanked us for improvement of the temperature operating conditions. The significant temperature effect of such a shielding and transparent facade has been confirmed. Finally, we unscrewed the extrusion profile to the requirement distance and we achieved the required 3D effects of the facade. The complete assembly of the facade, numbering 6 people, took 21 days. We also considered the satisfaction of the architects and the client with the realized work to be success. As another implementation, I chose a 2D facade of the parking house in Pec pod Sněžkou. Year of realization 2020. The area of the facade is 1200 square meters. The fabric used is TF 400 and the anchoring strips PTS profile, aluminium 80 by 40 millimeters. The architect's request was for the concrete parking house to be given a design code in the spirit of Sněžka. Here too an implementation problem arose. We were allowed to divide the longest and visible part of the facade into only 3 separate areas. which did not meet the strange parameters of convention anchoring system in connection with the facade area. Statical engineer Peter Feynman, his calculation and testing of samples took place again. Together with the designer Jan Vecko, we designed a supporting anchoring of the facade, which made it possible to fulfill the wishes of architects. Another requirement was to comply with the standard of ventilation of the parking house. We managed to achieve this by combining the offset of the textile facade from the building structure and choosing a fabric with a larger opens profile. The realization of the facade took 18 days and 5 people. Thank you guys. Bye.
Thanks to Lubomír Konečný for his lecture on the topic the use of membrane materials on facades application. Following lecture of Brendan O'Mullaney will introduce his amazing project Camp Sarika by Amangiri.
Hello everybody, my name is Brendan O'Mullaney. I own a company called Tent House Structures. We are based in Cape Town, South Africa. And I've been in the luxury experiential lodging and architectural fabric structure design space for about 25 years now. Today, I'd like to talk a little bit about a project that we completed last year. But first, just a little bit about my company. Tent House Structures specializes in the design, supply, and site assembly of luxury tented camps and lodges into Africa and beyond. Tensile membrane roof structures are the core infrastructure offering, to which we combine thin envelope enclosures, canvas mostly, insulations and so forth, delivered in flexible design-to-build solutions. I'm going to dive straight into it. So Camp Sarika was a project we completed for the Amman Resort Group, a prestigious wild resort group based in Asia and the United States mostly. This project was an extension of an existing and rather iconic hotel in Utah, in the Grand Canyon. They were looking to create a tented add-on to the existing hotel. We were appointed as the tent technologists. We collaborated with some very accomplished designers, local engineering, manufacturing and construction teams to create this extraordinary project. This project is set in the Utah, the Rocky Escarpment in the Utah, very beautiful views of Lake Powell and the surrounding escarpment, wind sculptured mesas, big sky backdrop of the Colorado Plateau. I would say that Camp Sarika is a masterful work of nature adaptive form and function. Historically, the Amangiri Hotel had tried to introduce some tented concepts into the area. They'd use teepees and other rather fun and quirky tented concepts, but really this sort of glamping approach was not aligned to the luxury brand of Aman Resorts at all, and they soon lost interest when damp and wind deterioration and other comfort issues developed. And they were looking for a more long-term, high-performance, all-weather product. So Tendal Structures was approached. They discovered us via our groundbreaking work on the skeleton coast of Namibia on a project called the Hoanib. And we were asked to reproduce this type of concept in Utah, but obviously technically this did not make much sense because the product we used in Hoanib was a flexible, stretchy type of membrane, which is fine there, but not in a snow load environment, and certainly not in a project which was looking for 20-year sort of lifespans. They needed something superior. So we decided that tensile membrane technology was definitely a preferred roof tech to the stretch membrane technology for this project. We were up against some well-respected US-based firms and were able to win this project, not so much on the price, but on our experience and specialist knowledge in the detailing and creation of luxury wilderness lodges. A strong understanding of the guest experience and what works well in the wild. So the brief to us was as follows. Our scope as the turnkey tent specialists was to form, find, engineer, specify details, supply, and install the tensile membrane roofing structures and the full canvas envelope inside and out. We were further consulted to provide the steel frame modeling for manufacture in the USA. So already there was this blended, integrated service and supply component which had to be very carefully managed in order to give the client a cost-efficient product and a product that allowed for enough local skills and materials to be introduced to the project, as well as drawing on our specialist expertise. So it was a real alignment of an international team of Africans and Americans. We had to produce a prototype on the site for both the architects, ourselves, and the contractors to proof detailing, test run performance capabilities over a full season cycle and optimize the construction process. Prototyping in our business is, especially for these one-off iconic projects, is really essential because you're going to be delivering not just one product, but a series of them. And if there are some flaws or some functional issues with them, you don't want to be repeating that. So the guiding principle was to be as efficient, i.e. lightweight, as possible, with no compromise to aesthetics and performance standards. So this leads me to what some of our technical challenges were on this project. Firstly, the tensile membrane roof structures. Tensile membrane form and engineering is an iterative and integrated discipline. As Fry Otto calls it, a bionic design, where form and function are inseparable and influenced by multiple factors. The key factors at Camp Sarika were the design demands and limitations. Number one, the building code, of course, the imposed safety and shape factors for the state of Utah, the high winds, 90 miles per hour, a fairly light but nonetheless existing snow load of 6 pounds per square foot, an exposed terrain and wind funneling, some extreme temperatures, the range of temperatures, which is quite typical in the US actually, in Celsius ranging from -15 or -20 to 45 degrees plus in summertime. And of course, that also impacts on the fabric's temperatures, which are minus 20 to 90 degrees Celsius. And then just the maintenance of the product was also a bit of a technical challenge. All of these presented a substantial set of challenges to the frame engineering, the cable support elements, the membrane fabric, the shape, the size, the detailing, and deflection behavior of the membrane. Just a little bit on the bionic design challenge. Flattening the roof to the allowed maximum height out of the view of the main hotel was a requirement. It limited the amount of curvature we could build into the membrane system. And as we know, the more shape, the more curvature, the more the ability of the membrane to resist live loads. This in turn influenced the fabric selection and reinforcement techniques, as well as access to and views from the suites. The shallow roof angle and membrane deflection would result in ponding and the membrane touching the structure beneath. How we overcame this was to reduce the height of the perimeter masts, extend the canopy out beyond the enclosure beneath, and introduce under-fabric cables, and then cut dramatic, strategically positioned scallops along the edge to avoid ponding and to allow entry and light into the area. Another little comment on some specific detailing challenges. As Simon Chu calls it, the tarso, which refers to the engineering design of connection points in tensile membrane structures. Tarso is critical because it affects the entire structure's stability, durability, ease of installation and maintenance, the aesthetics too, and the cost. So vector-aligned connection systems, swaged cable ends, high tensile steel U-bolts, specialized washers, fabric reinforcement techniques, all considered. Then we have the aesthetic and performance of product. Working with the architects, we selected neutral fabric color palettes that complemented the surrounding environment, tent architecture and interior design. This is a very important part of our process. We're working in a wilderness environment where we need these discrete and harmonious colors and textures and shapes. Often quite hard to secure and combine and produce with fabrics that also need to perform at the same time. Nonetheless, this is, as a business, what we do. So the roof, the ceiling, and the wall systems at Camp Sarica comprise of 3 layers, 3 different fabrics. Layer 1, the outer membrane, is an architectural PVC. In this case, it was a Serge Ferrari Type 2 PVC with a matte finish and a PVDF coating on it. Over pretty soon, in a desert environment like this, the surrounding dust settles on these outer membranes and that shiny synthetic look disappears very quickly. And actually they take on a beautiful natural canvas look quite quickly. Layer 2 is what we term the hermetic ceiling and the exterior walling. So this is what you would see from the outside of the enclosure. So the ceiling and the outer walling are in a technical canvas that we produce in South Africa. This is a very durable skin with 20, 30 years of tried and trusted in the African bushveld, It's fairly easy to maintain. It can be painted if it fades in terms of coloring or gets stains on it, and it's quite a cost-effective product. Layer 3 is the interior ceiling and the wall linings inside. This is a strictly interior detailing, but nonetheless, this particular fabric is a fabric that is a proprietary fabric of our company, which we've developed over time to imitate cotton, but in a polyester with all the right and necessary fire retardancies and so forth. It's a textured weave product which we pattern into the ceilings and onto the walls. Very important, this is a very high-end finish. Seams need to align, and the detail is where it all happens. Obviously, all our fabrics have to meet the correct fire retardant standards in the United States. The NFPA 701s, the California State Marshal fire retardant standards. All fabrics had to go through the biaxial testing for their modulus characteristics under specific pre-stress and design life load scenarios. And in collaboration with our textile partners, Layer 1 and Layer 2 were developed with built-in heat shields to block all transmitted light energy. In this case, in our business, translucency is not always your best friend because of dust and dirt, and with the darker fabrics particularly, we want to really optimize our optical properties to reduce any kind of, to reduce heat transfer. Layer 3 was developed, the ceilings, to emulate the soft handle and texture weave of a duck cotton canvas, as I've said, and other tropical treatments for easy maintenance and dimensional stability. A little bit about the integrated building systems. So the frame itself, Tendile Structures, we engineered the steel roof trusses and the piston masts to fit onto a timber subframe made locally in the United States, and the outriggers to tie into submerged footings. Working with local structural engineers, we integrated the steel with the timber to work as a homogeneous tensile system. Connection detailing and complex structural behavior were resolved. Tensile membrane engineering is obviously a precise discipline. The construction of the perimeter footings and frames was set out according to design and surveyed post-build. That survey information was relayed back to our engineering team, whereupon we recalibrated the membrane system design to as built before we manufactured it. This is always a challenge with sort of high-end projects with a free exterior, an uncontained system where you've got tie downs which aren't returning back to a frame as such, as you have to go through the survey process, and this can often hold up procedures, and it's in our business, time is money, because every day that the hotel is open is a day that they do not have revenue. So we have to develop very close relationships with our international partners to ensure seamless and smooth delivery of these collaborative projects. In terms of the envelope, our canvas linings and claddings were detailed to connect to the timber stud wall envelope in this case. This entailed such complexities as lace tension ceilings, top-fitted wall profiles, ring beam profiles, and canvas-clad corner trims and eave valence systems. The hermetic ceiling, the exterior ceiling, had to be fitted onto non-orthogonal timber faceted surfaces with custom extruded profiles. This was quite complex because as much as we tried to resolve this in the design phase, because all of this is made off-site, working with local contractors was the challenge was that we are used to working with very fine tolerances and local contractors not so much. So once we got to site, our team of specialists had to make quite a lot of adjustments to the timber surfaces to make sure that system lines were correct and so forth. So altogether there were about 6 key role players on this project, between South Africa, the designers and the 10 technologists, ourselves, the architecture interiors, and then the Americans, the client, of course, and the steel company and the contractor, the general contractor. Another great challenge of working in foreign environments, which is something we specialize in, is the imperial versus metric systems. And it sounds like, why would that be a problem particularly? But it's working with engineered systems and fine canvas details does require a high level of discipline to convert from metric to imperial and back again. It's not a learned behavior if you're used to working in one or the other. The consequences of conversion errors can obviously lead to misalignment of integrated systems or system failure. So this is something we obviously to monitor closely. And then the other challenge is time zones. Working with time differences between design and field teams in both South Africa and Western United States requires a committed approach, rigorous forward planning, and after-hours contactability. Okay, so some of the other challenges that we faced is we handled this somewhat of a turnkey process here. So we're engineering, we're detailing for fabrication, we're manufacturing all the soft components and specialized tensile components, and we're handling all the logistics for this. Consolidating, packing, labeling, export manifests, loading, sea, air, and road freight, and debunking it on the other side. And then once we've done that, our specialist site team arrives on site and works with local appointed contractors and labor under our guys. Navajo Indian teams, American teams, Mexican teams, a real collaboration of cultures and people. The site operations for this type of project are extensive and highly specialized service. They cover storage, preparation, programming, crew supervision, tensile rigging, canvas fitment and snagging. And this is all in a remote environment. Whereas, say, in an urban environment, if you're short a tool or some hardware, or you need to, you've got a power problem, it's generally resolved quite quickly. In a remote environment, that problem becomes increased by an order of magnitude. So it requires an enormous amount of planning, but it also requires a certain type of individual who is used to and experienced in working in challenging environments. And our team of South Africans have built lodges throughout Africa, and very used to these kind of challenges. Rigging the tensile roofs, in this case, these large span membranes are vulnerable to wind and snagging damage during erection, which is typical with all tensile, large span tensile structures. The difference here, of course, being that the environment is a little dustier, and the equipment available is a little bit more simplistic than one might necessarily have in an urban environment. The expert rigging team from South Africa and North America, our expert team, planned accordingly for these conditions. Some of the planning involves the following techniques: saddle strapping the membranes along horizontal boom rigs, lowering them onto position over the cones with one man positioned at each cone head, fixing the cone heads with membrane partially wrapped to avoid flapping, then rapidly unfolding the membrane during calm conditions with one man per connection point, This is obviously a critical period. Then connecting the perimeter points to pre-installed masts, raising the membrane, and achieving a first fix in one rapid contiguous process. This ensures the entire membrane had enough pre-stress to afford adequate structural stability for the now protracted final fix process. A little on some troubleshooting that we have to deal with at Kamsarika. The locally constructed shell, as I mentioned earlier, was a typical North American OSB-clad stud wall frame with a polyurethane insulated fill. The as-built versus the design tolerances were at times beyond the tighter acceptable tolerances for pattern fabric systems. Our expert technical supervisors were able to make complex on-site corrections to the shells and to our interface systems. This hands-on problem-solving approach comes from years and years of experience developed building in the bush in Africa. And just lastly, a little word on team culture. As with all of our tent house structures projects outside of our home turf, cultural assimilation between professional and site teams is a valuable soft skill developed over the years of working across borders. We, in fact, relish the opportunity to work with people with different backgrounds. And in conclusion, these iconic tented style suites in Utah are pioneering the future of performance fabric technology in the United States eco-hospitality landscape. We answered the brief with iconic, efficient, high-performance structures where the guests can intimately reconnect with nature. This is Kamsarika. Thank you very much, and I look forward to hearing your questions.
Brendan, thank you so much. You have made a wonderful project. It's fresh and inspiring. Thank you again. Now, next presentation comes from Chile, and Felipe Alvarado will present us the company and his work, the company Espacio Cubierto.
Good morning. My name is Felipe Alvarado, and I'm the technical manager in my company Espacio Cubierto. We develop all kinds of tensile structure in Chile. So first, I'd like to thank to the organization team for this invitation, and maybe apologize for I have a little flu or something, so maybe my voice is not so comfortable. So the topic of this lecture will be about the fabric roof supported only by existing buildings. So it means no other kind of structural elements to make the stability of the fabric. So it will be only tensioning to the existing surrounded buildings. Okay, there are many classifications you can find for tensile structures, membrane structures, and so on. So one way to classify is how they are supported, or how the main structure is made, how is the stability for the complete system given. So in frame structures, you can find very complex and massive, innovative kind of frames, like tree structures or simple soft arches. But anyway, they are based on the stability like a classical way, more or less classical way. So the membrane makes like a softener or complementary structure to the main structure. Strut embracing is more or less the typical or the better known way to develop tensile structures. It necessarily includes compression elements known as mast, and the structural stability depends of the correct or consistent behavior of these elements. Let's say a mast must be rotated in the base, should be free for rotation, and the cables, of course, has to be in the correct tension. So the topic we will see in this lecture will be based on fabric only structures or structural fabric. It depends basically on the fine and accurate definition of the site. It's a geometrical and the technical problem, and of course the stability in case the existing buildings are not made for resistance to resist the tensioning out of the walls, but also for a very accurate or a proper definition of the fabric issues itself, like proper compensation and installation method. This is a project we made for Universidad Católica in Valparaíso, Chile, and as you can see here, is surrounded only by existing buildings. So here you can find a straight borders, and then it comes to be more flexible or free cable borders, as you see here in the video. So you have to look for consistent definition of the fabric itself, like compensation, as I say, and also for reinforcement, like these membrane plates in the corners, and also to keep on the lightness of the complete system, including the compact or reduced volume in order to be transport and storage, for instance, to keep the small package. So first project I will show you is Escuela Simón Bolívar in Santiago, and this picture show you about the physical context for the covers we lately create. As you can see, there is diverse but little heterogeneous context, but surely all concrete. So the only architectural requirement was to keep continuous cover between the corridor and the new covered area. Existing corridor is in the back side of the picture. As you can see in this picture and the next one, there is one free side with no possibilities to be anchoring. So we have a bigger span to cover. So the conditions are like you can see in this top view, one building with this particular shape, rounded corner, and no chance to be anchoring in this building over this side. So this is the late picture with the cover already installed. So we can see how we put a pixel in this urban context. So the initial information given by the client, as you can see, is not very much information. Just put a cover over here and you cannot figure out from this requirement what kind of shape you can introduce over here. So later we had better plans, but anyway, we had to figure out how to make this the existing building from this existing information, like regular or printed plans. So we figured out how to make the context in order to have the model in the computer, and then start to figure out what kind of solution we can propose to the client. So in this very early stage, we figured out we need more shape because the cover is too flat, as you can see in the picture. Anyway, it was useful to realize where are the key points to be worried in the surroundings. So here in the early stage, we can see the possible solution about the how to reduce the complicated situation in this wide span side. So this is more or less the final version, and here you can see we introduce an extra catenary in order to make even bigger the cover area. Also, we add another one here. So you have one floating plate over here and two floating plates over here. So as you can see also, we add an extra valley cable, which is maybe the most characteristic of this cover, because I feel it's so dramatic compared to the another version is too flat, and this is good shape, good double cover to shape, and we make all the effort to reduce the gap also in the corridor requirement. Like we couldn't cover everything because we have to mind also how the membrane should be developed. So we make the big effort possible and make just a small gap near to the corner. So then when we had the proper shape, we like it, architectural and the performance for raining and for sun protection. We make the statical analysis with the all kind of internal and external loads. Internal, let's say, pre-stress and self-weight, and external, let's say, wind and all the loads are required for a normal engineering project. It's given by the code for sure. So here you can see that there is different load conditions according to what is described in the code, and you can see there's where are located the biggest tension in the system. So as would be expected, the big span will carry also the bigger forces. So here you can see there is a different load cases. This is for pre-stress. Everything is in tension in the blue numbers. Everything is all in tension, but also in different kind of load cases also is in tension. In any kind of loads, no matter if the loads are going to pressure, like going in direction of the cover or going outside the cover, no matter what load cases, always the system is the stability is given by tension forces only. So that is very nice to see after how the consistence model continues. So then we start to install the supporting plates. You see that they are not very small, because the wall, in my opinion, they look better if they are smaller, but we couldn't make it smaller because, as you may know, the walls, they are not designed or pre-designed in order to be pulled out from a tensile structure. They have to be worried, or they have to be reinforced from the beginning. In this case, from the construction of the wall. I mean, in this case, the building has many years before, like 30 or 40 years before made. So in Chile there was no tensile structures in those days. So we start to put all the points according our system, but then anyway we have to be very careful to topographically describe how the points finally were installed. So because if we are not very precise where the points are, we cannot manipulate very much the form. So we have to be very precise where the points have to be, or they are located, and because the fabric have to reach that point exactly. So general visualization of the project, but of the plans, and here you can see there are very simple layout for fabric. The only two zones, and here you can see the valley cable curvature more dramatically. So in those days we didn't have the plotting machine for fabric, so we had to do it in traditional X and Y coordinates. Nowadays we have a plotting cutting, so this step is easier, but you can do it anyway. This is for encourage you in order to put hands on and figure out classical method to continue the production. So here is the final result. As you can see, there is very much more cover area, of course, and here you can see the two plates, floating plates, where they can protect or cover a little bit more. One nice challenge was to avoid this ventilation tube chimney. We also was very carefully to describe it, the position, and in order to be near more or less 200 millimeters. So after all of this cover, to about 300 square meter, we reach all the borders carefully and precisely in order to have proper stability for the cover. As you can see, there is no compression element involved. Here, this is the continuous space they require for between the corridor and the new cover area. So the second project I will show you is one I like very much. It's maybe one of my late favorite project we have made, because it was a good chance to to develop or to get new challenge on our regular work. As you can see here, this is the context. So you can see these novel pagodas, and the client wanted to avoid, and they give and they wanted to have a total reconstruction for this internal courtyard yard. Sorry, both. As you can imagine in this one, in the two contexts, it was not possible to include a big crane or some machine cranes in order to do the installation. So everything was like with the scaffold and very carefully treatment. So as you can see here, well, the client wanted to change this context and make it a more spectacular place to live. Here you can see the urban context. This small area is what I'm showing. You can see there is surroundings for 4 sides in this case, and only trespassing corridor for people. Only people like 2 meters wide or something. And here you can see this picture is a nice picture because it shows several projects for our company made in the same part of the city. I didn't realize before, so I was looking for the picture in the Google and then realize I can show you a wider scenario. So we make also this stadium. This is the Dalka Stadium. You can find more information in the site, in our site. Okay, so this is the more specific context, and this is the small corridors. As I told you before, we just put the we just enter to the site by this site. So okay, different proposals. Also, this proposal was too flat. Was not possible to give it like that because we needed to have more different heights, and we in the set also leaves so much space in between with no cover. So a big effort to put such amount of material and energy and having maybe the half of the cover without shade. So here the local context is a little bit more heterogeneous, as you see in this picture. There is glass, there is different kind of events or situation to attend, like this camera and some lightings and so on, and different kind of materials. So this surrounding was a little bit more complex in the small details to attend. Also, as you see here, there is a fountain. We need to know what to do with it, if it's possible to use it or not. So the context, as you see here, well, we try to copy ourselves before than we showed what I showed you before, but let's say it's a economical solution in order to make again something you have made before, but it comes some problems we didn't want it to have, like collecting water to the sides when the people is walking. So then for the reason to avoid this water to the sides, we needed to collect the water to the fountain. So a cone appears, this cone shape, inverted cone shape appears. But we wanted to have it, we wanted to keep it lighter, even lighter. So now the mid-rings was very heavy. What was the heaviest element in this cover? So we thought we were possible. It is possible to make it even lighter. So we look for this eye loop detail in the center part, and we look for reference in the internet, but not specifically, very much specifically, but what we wanted to solve or what we wanted to propose to the client. So we had to make our own version for this classic eye loop shape. So we had the chance to start to figure out how to apply it and how to make all our knowledge in membrane manufacturing. So the loads also are applied, as you can see here. Well, this is the pre-stress and pre-stress and self-weight state, and here some loads are applied to the cover. As you can see here is the suction wind loads, wind up, and they're more or less the forces. As you can figure out before, as you can figure out from this scheme, you can see the biggest tensioning is in the center part. So then we have to make the plan for manufacturing, also very simple, just rectangular like shapes in order to recreate or to manufacture this as tuning cover. I don't like very much how it's look for us. Oh, sorry. I miss. Sorry, I miss this picture here. Sorry, I missed this picture here. It shows how it looks for the upper part. I don't like very much how they look like. As you can see, it's like the shape cannot be very simple appreciate from the upper part, but from inside is more beautiful, I think. So then we start to, as you can see here in this picture, all the system, for installation system this is very simple, because you only need to hang the cover from the upper point, and then to pull out in the center, in the center mid cable. So it's very simple for installation. And then as you can see here, there is a orchestra or something happening down the cover, protected by the cover, and then the client came with this the requirement to cover the loop. So we almost wanted to cry because we found this solution very beautiful. And suddenly the client say, no, it's too big. We wanted to cover. So we call this the funnel. The funnel is the cap solution for this for this project. I wasn't very sure to show this picture, but I think the final solution is accordingly with the initial cover, so they look alike. It was not so bad. Okay, I will quickly show you this another another project. Well, the last project I show you quickly. You can see also this pagodas like a solution for shading, but you cannot have a homogeneous, continuous architectural place. So they have also these vertical covers for this corridor place. So they wanted to have something more complete. So we start to figure out how to do here. As you can see here, we put a continuous border over these frames. You will see later, and you see there is a better understanding how the place could be enlightened. So here we put all in practice what we have done before with the different possible collisions, like in this case is a palm tree, and we get more confidence how to develop with this kind of project. So these straight borders, as I show you, guarantees that the student will be the student mobility will be covered also. So there is no gap areas for covering, and also we leave some spaces near to the existing walls in order to make grass growing in one side of the project. So one side is very watertight, also here, very watertight, and the other side is very open or more free. So I'll show you a video about this cover. So, well, you can see the palm tree in the middle of the two tensioned fabric, and the water collection is in the middle of the grass of the middle, and you can see how now the whole space can be used for relaxing and for courtyard and so on in the place. So nice to see how the nature still is in the place. The existing trees, they still are in the courtyard. So I would like to thank you very much. I know this remote presentation allows you to be present there, and but also make more difficult the communication or the interaction between us. So I invite you to visit us and to send me any question you have. I'm the responsible for the calculation of the 90%, almost total structure of my company. So if you have any question about this, what I show you in this presentation, or any other, you can visit our website, and please let me know your feedback or questions. So no more to say. I would like to thank you for the attention, and hope you can enjoy this presentation. Bye.
So many thanks to Felipe Alvarado for very detailed description of his projects made by Espacio Cubierto. There are some questions from the second part from the third part of the conference. So I will read the questions. They are up to Brandon O'Maloney. He's not unfortunately online now, but he did answer on our Skype chat. So I will read the questions and I will reply. So there is a question. What is the current project you are working on, Brandon? And the answer is currently building a royal winter camp in Qatar. And the second question is just a moment. What was the most challenging project he was working on and why? So that was Congo Tufts project in 2008. So maybe for further information or detailed, you could visit the website of Brandon. So now there we go to have another last lecture, last video from Simon Chu, who will present you like now. So enjoy the presentation of the video.
Hello everyone, welcome, good evening. My name is Simon Chu. I'm the executive producer of this documentary film, Fly Auto, Spanning the Future. I'm grateful to be included on today's Architecture of Lightweight Structures conference. Thank you to the Czech Technical University in Prague. I started making this film back in 2012 when I was a PhD student at the University of Southern California. It took about 3 years to complete. It was one of the last in-depth interviews of Fly Auto before his passing in 2015. The film was done on site in Stuttgart, Mannheim, Munich, London, and Los Angeles. Since the film was premiered, it has been screened at over 50 film festivals and university and professional conferences around the world. There may be a chance that you have watched that before, and if you do, thank you for watching it again. If you have any questions or comments, please feel free to contact me via the website flyautofilm.com. Thank you for having me, and please enjoy.
People like Fly Auto have a kind of a longevity in terms of ideas, because these ideas were very avant-garde at the time and very progressive. And so therefore, although as 40 years ago, they still are very refreshing.
As our work matures, we have much more in the footsteps of Fly Auto. Whereas before, we were radical and new, but in retrospect, compared to Fly Auto, perhaps superficial.
biggest enemy of building is man.
Auto has shown us how it could look like if somebody is really doing it as an artist, not just as an engineer or an architect, but as an artist.
He liberated architecture from kind of square and rectangular kind of forms to really make forms which are in response to natural forces in nature, so with minimum amount of material.
We can study the nature so that we can be a part of her.
He brought together engineers, architects, biologists, and the most different fields that even were not connected at this time with architecture.
I am also a writer. You could say also a sculptor. You can tell me also as a philosopher, a painter. I am nothing.
Frei Otto's work in tensile structures is staggering. He's really the father in so many ways.
Frei Otto, spanning the future. Over half a century ago, architect and engineer Frei Otto became world famous as a pioneer in the design of tensile structures. Born near Chemnitz, Germany in 1925, Otto's life story is set against the sweep of European history.
I raised in Saxony. My father had a beautiful workshop with a large ground, and I raised up with many animals of all different kinds, sheep and pigeons and chickens. And my mother was especially favoring nature, so that's not a problem for me. I don't know a human being who has not interest in nature. My father was a sculptor. My parents have been members of the German Werkbund. This was a driving force in the 20s for modern architecture. Mies van der Rohe and Walter Gropius have been directors of the Werkbund. And so I was just in the picture of the new movement in architecture as a young man.
The tragic events soon to unfold would derail the development of modernism in Germany. Beginning with the rise of the Nazis in the 1930s, their ultimate defeat in the Second World War in the 1940s, followed by the reconstruction of Europe in the 1950s and 60s. While studying architecture in Berlin, Otto, at the tender age of 17, was drafted into the Luftwaffe, becoming a pilot.
I have seen whole cities burning. As a pilot flying over the burning cities, especially the city of Munich, the city of Ulm, and also partially the city of Stuttgart. To talk on those things, to learn what you could learn from a war, is very important. The strongest first semester for a student of city planning and architecture is to see a burning city. You will never forget that what generations have built and made and developed could be in a few hours destroyed. The question is still the same question since after the last war. What you have to do to survive. Yes, my architecture is an architecture of survival. Very simple. To survive also with all what we are doing.
Captured in 1945, Otto became a prisoner of war in France. While imprisoned, he began to create makeshift tents out of sheets and blankets. The need for shelter in a circumstance of material shortages would be the conceptual underpinning of his life's work.
I must say the philosophical aspect of my work, coming of course out of the 20s of my family, is to make not only a new kind of architecture, to make another architecture. Under Hitler it was a very strong, heavy architecture. And I, as a young architect, wanted a new kind of thinking, real new kind of thinking.
After the war, Otto studied briefly in the United States. While in the U.S., Otto met with, among others, Eric Mendelsohn, Mies van der Rohe, Richard Neutra, Frank Lloyd Wright, and, most significantly, Buckminster Fuller, a fellow traveler in theoretical structural engineering. Returning to Germany in 1952, Otto completed his studies at the Technical University in Berlin and established his practice. Frei Otto was awarded his first significant commission just a few years later, when he was hired to design structures for the 1955 Federal Garden Exhibition in Kassel. The tent was executed by L. Strohmeyer and Company, a firm that since the late 19th century had made tents for circuses, festivals, and for the military. Otto worked directly with Peter Strohmeyer, then the head of the company. Together they developed a new material, membranes pre-stressed via embedded cables, which maximize the stiffness of the fabric. With the three structures at Kassel, the music pavilion, the mushrooms, and the butterfly, Otto established his reputation as being chief among the pioneers of tensile architecture in Germany.
These have been a new kind of tent structures using membranes. And I was very lucky to have in the tent firm Strohmeyer. Strohmeyer was in this time the world leading firm in tents.
Together with Strohmeyer, he made the design, Strohmeyer built it. Then there was a development of tent buildings, of membrane structures. And then with Frei Otto, he started to develop a much more sophisticated way using membranes for architecture.
The Kassel tents led directly to those built for the next Federal Garden Exhibition, held in Cologne 2 years later in 1957. For Cologne, Otto designed 4 structures: the entry arch, the hump tent, the peak tent, and, most significantly, the dance pavilion, which was completely surrounded by a fountain. The dance pavilion, though intended to stand for a single summer, has been retained to the present day, with its membranes having been periodically refreshed.
But his structures were remarkable at the time, particularly the contrast of these super light dematerialized translucent surfaces which span quite large spaces compared with the heavy stone structures.
What really impresses me the most is the force of innovation behind his thinking, both in structural geometry and materiality.
But it was congenial to some extent to the ambitions of the 1950s modernism, which picked up from the 20s, for a light and dematerialized architecture. So the work of Mies van der Rohe comes to mind, the work of Egon Eiermann, but they did this with orthogonal systems, with steel and glass construction, and Frauto just was beating these efforts by orders of magnitude in terms of dematerialization.
Also in 1957, Otto became involved in the design for a number of structures at the Interbau in Berlin, which was an international architecture fair. His most important contribution to Interbau was the Garden Café and its complement of 4-point tents. The roof of the Garden Café was made of a single piece of Perlon fabric, held up by only 8 masts. The Garden Café became an international sensation. Otto's theories about the portability of tensile structures would be tested when the hump tent of the Garden Café was moved in 1958 to a man-made island in Lake Zurich.
This combination of the hump tent in the water, in the park area, was a sculpturing highlight.
These little things are much more impressive than the huge ones, you know. Even if the huge ones are based on the little ones. Because the knowledge taken from the little ones, experimental small buildings, have been the basis to build the very big things.
Based on the knowledge he had acquired creating these tents, Otto designed a pair of monumental tensile structures and a number of smaller ones for the International Garden Exhibition in Hamburg in 1963. There was the enormous wave hall and the membrane hall, which was even larger. The forms of these structures were theatrical and lyrical, qualities that were heightened by the equally dramatic smaller accent structures, the 4 cross-wave pavilions. The culmination of this first phase of Otto's tensile experiments were the Liège rock tents he created to serve as the roof of a pavilion designed by architect Marc Sauguet for the Swiss Regional Expo of 1964 in Lausanne. The Liège rock tents represented a breakthrough for Otto in his quest to span wide areas with tensile structures. And the Liège rock tents would lead directly to his first truly international triumph, the German pavilion for Expo 67 in Montreal, which featured the rich vocabulary of forms he'd been developing for over a decade. Otto began work on the pavilion at the Institute for Lightweight Structures in Stuttgart. Initially, Otto had the faculty and students at the institute create a full-sized model of one of the tent structures that he envisioned using for the pavilion. When all the necessary testing had been fully carried out, this large tent was converted into the permanent home for the Institute for Lightweight Structures, which is still standing in Stuttgart. Using a series of physical models, Otto conceived of a megastructure for Montreal. with the German pavilion having been imagined as a lyrical clutch of assembled tent forms. Their specific shapes and relationships determined by a dialogue between the structure and the natural forces. Otto combined the dominant tensile forms with a partial interior grid shell hidden from the outside by the tents. Otto employed vertical steel pins anchored into the ground, which were then draped with a wire mesh, the entire structure being ultimately clad in a translucent fabric membrane. Constructed on a series of islands in the St. Lawrence River, Expo 67 became a showcase for cutting-edge ideas in engineering and architecture. This made the selection of Otto as the designer for the German pavilion a logical choice, since at that time he was the most revolutionary designer in Germany.
I was known as the young tent builder, and I was very happy that I was asked to build this building. I made several model structures and tent structures to make this pavilion.
One way, Montreal represented kind of like a break, because it was built, designed on Freude's theory of building models. And at the same time, Montreal was really the first building was built based on physical models, but also based on computer theory.
Pavilion was pretty large. By 100 meters, this time was unknown to have a cable net or a similar structure. Now it was steel cable net. The first time on a large production with a cable thickness of 12 millimeter. Without Peter Strohmeyer, the tent builder, I never could have done this pavilion. I was very happy to have the best producer and scientists of tent buildings behind me.
Expo 67 was presented from April to October of 1967, and it caught the popular imagination of the world. There were the mini-skirted hostesses at the British Pavilion. There was the unveiling of a new Alfa Romeo sports car called the Montreal. There was a live broadcast of the Ed Sullivan Show. One of the main attractions was the open-air monorail that took visitors throughout the site. And setting the architecture press on fire was Habitat, a radical high-rise made of stacked, pre-manufactured elements by Moshe Safdie. But most of all, there was Buckminster Fuller's geodesic dome for the U.S. Pavilion. Otto, who referred to him as Bucky, was a close friend of Fuller's.
I loved him, and we tried many things, and this was our real relation. We both did think free.
Inherent in doing more with less is someday you might be able to do so much with so little per given function. You might be able to take care of all humanity at a much higher standard of living than anybody's ever known.
Look, one sentence of him: I could build a grid shell around the earth. He said once to me, but he expected that I said to him, You could not do it. Maybe with a satellite of 100-meter diameter or 1 mile diameter. But you are wrong. You could not envelop the Earth. And 2 years later, I met him in Berlin. Then he did come to me and said, "You are right. I cannot do it. I have understood the limits of structures."
So it's a minimum system in the universe, and only a triangle holds its shape. And I want to have a word, I want to define structure.
Bucky Fuller was kind of pioneer in lightweight construction, and when he asked Norman Foster once, "What does your building weigh?" And Foster was kind of dumbfounded, couldn't answer the question. But I think Otto would have known, and most probably did the lightest building relative to surface coverage that was ever created up to that time. I consider Otto to be, in the end, much more profound and important than Bucky Fuller. So Bucky Fuller was stayed, in a sense, with Platonic geometries and didn't liberate form to the extent. He was pioneering in the sense of being anti-classical in material translation with his geodesic domes, and he had a geometric knowledge and innovation. But what Freud is doing goes beyond geometry. It is this material computation which allows form to find itself, tying in with the infinite or endless forms of nature. Whereas Bucky Fuller stayed with the Platonic solids, if you like, of classical architecture and didn't go beyond that.
He has built only a very small number of buildings. But he has his influence was intellectually, philosophically, and not in that way that he has created examples which the rest of the world, the rest of the architects and engineers should follow.
But what is so unusual about these tensile structures is their scale and their free form, the capacity to not be constrained to symmetry or one single cone like TENS used to be, but to have multi-pylon complex networks and resolve these complex balance of forces. That makes them so unique and beautiful, and then he translated that into the much larger project at the Munich Olympic.
Even as the finishing touches were being put in place on the German pavilion at Expo 67, Otto received the commission for what would be his most important undertaking, designing the complex for the Summer Olympics to be held in Munich in 1972. The Olympic Village competition represented the most sought-after commission in Germany since the end of the Second World War. Many of the most prominent architects and engineers then working in Germany were involved in this ambitious project. Otto teamed up with architect Günter Behnisch to create the master plan. Otto then reassembled the team of colleagues he'd been working with for years. There were the students and teachers from the Institute for Lightweight Structures. There was Peter Strohmeyer, whose family business had been making tents since the 19th century. And there was longtime Otto collaborator Fritz Leonhardt, a structural engineer, who brought in Jörg Schleich and Rudolf Bergermann, and there were many others. The site chosen for the Olympics was redolent of modern history. The area at the edge of the city, now known as Olympia Park, is covered in hills sculpted from the mounds of rubble moved there after the heavy Allied bombing of Munich. The cutting-edge design of the Olympic Village, rising as it did on these evocatively fallow grounds, eloquently expressed the key goal of the Games, to recast Germany internationally as a peaceful and modern nation.
When I did work for the Olympics, there was no change in personality. It was nothing new for me. It was using the given knowledge in this time.
I was about 15 when the Olympics in Munich took place, 1972. And the competition for these Olympics had been done between several people. My father, Günther Benisch at the time, Benisch and Partners, together with Frei Otto. And what was interesting was a very holistic approach. The engineering, the landscaping, the sports, the architecture, it was all one thing.
But there was for many years always a kind of conflicting relationship which was maybe a little bit based on jealousy. That the engineers felt, how come architects get all the credit and we do all the work for them? So, but then eventually they ended up working together very nicely.
We should not forget that at that time they were all very young who were involved with this project and had submitted a competition entry with a structure, an architectural image that never had been done before. It was a very unique approach. The only time something similar had been done was for Montreal, for the German pavilion, which was similar but in a very much smaller scale. And for me, it was, for all of us, was a very exciting and tense time.
A lot of very interesting collaborations between all these people, you know. So you would find some, like 2, 3, the egos were always there, but they kind of overcome their whatever it is to do a great idea. And that was what's really exciting. I think that the tents and the Olympic side are really stunning because you don't expect it to have such transparency through glass, not just through fabric. That's really amazing.
One of my studies had been the largest span which we can do on Earth for all structures. Any kind of structure has a finite span. Only the tension structures has the largest span which you can do in the world. Compression structure out of stone, you could never do spans of several kilometers or miles. With tents, with cables you can do.
If you scale up structures, something also happens. There's, there's a difference between an elephant and a mouse. It's not only just an inflation of geometry, like the classical architecture thought. They said they had a proportional system, they can do small, medium, large without changing the proportions. That's one aspect of this, where he went large, he suddenly had huge members, and sometimes it has been kind of criticized or discussed that the lightness he achieves overground is actually achieved by incredible heaviness of foundations underground.
Not so easy to erect a cable net, which high weight, even if it's a lightweight structure, it's a high weight. The stadium has about 12 or 15,000 square meters, and it has to be erected with a special kind of scaffolding underneath to bring it up before it can be pre-stressed. And all these things have to be discussed, and how to put the cladding on it. All these things have to be developed together with the institute group, Prioritas group, and the engineers in Munich. We were left gravel and sand. And to anchor a tension force, that's one of the problems in pre-stressed structures. You have to anchor tension forces. Rock is the best ground, and sand and gravel is the worst one. And in Munich, it was a very bad situation for the foundations. All the cables guiding the mast top, they have to be anchored for tension forces. And that was one of the biggest problems, how to anchor high forces, high tension forces in a gravel ground. And it was made with heavy weight. The big edge cable of the stadium, the tension force in it is 4,000 tons for the normal state without loading. And to anchor 4,000 tons of tension force to gravel ground is only possible with at least 5,000 tons of weight on both ends. They had to build blocks of concrete in the size of private houses, compact concrete, to create the foundation to anchor these tension forces.
What is still magic is the transparency and lightness of the actual membrane, where you have equal spans with an ordinary, for instance, bending beam structure. Not only would have these huge columns as well, but we would have huge beams and members, while he achieves the kind of dimensionless, nearly dimensionless cable net. So it is super light still, but to feel the heaviness or the forces finally where they concentrate in the pylon, that becomes, of course, very large.
Part of the roofs were designed with computers, computer programs written specifically for these tensile and tense structures, and Frei Otto still worked with his chains, the chain models, physical models.
Actually, there were a lot of people who were kind of critical, or maybe not critical, but more skeptical, because they thought maybe it works, maybe it doesn't work. They were kind of questioning whether it works at all.
I have a particular liking to the Olympic Stadium. As an engineer, I find the inventory of all the tensile structures there to be incredible, right? I can literally find all of the kind of conditions you can achieve in that kind of a structure. And so in that case, in many cases, it's probably one of the best examples of built work where you can go and actually see the actual physical consequence of a specific approach.
His greatest accomplishment is rethinking the way we think about structural forces, in my mind. He envisioned a way to take on ideas about structural stability from the exact opposite. Instead of only thinking about compression, he really brought in ideas of tension and ideas of form-found structures, which are more common today, but at the time of his invention and operation were really quite unique.
This paradigm of parametricism I've been talking about, and where I said Frei Otto is the only precursor to it, we can maybe achieve a multi-author coherence.
The formal approach where suddenly the building form and structure, again, like in the old historic architecture, building form and structure became unified again, not separated. Where it's suddenly possible to form buildings that are with a structural supporting skin. And I would say that this approach, thinking approach, that structure and formal form in architecture are not separate elements, that they should be unified. I think that's one of the big merits of Frei Otto, to really not invent it, but reinvent it again and make it understandable for everybody.
And I'm surprised these ideas were not used more, and not just there, but in other domains, because there were so many congress centers, so many large spaces underneath, and this is, I'm really surprised.
Without a doubt, Otto's designs for the Olympics are what established his place in the history of architecture. However, despite the fact that the Munich Olympics, nicknamed the Happy Games, were meant to showcase a new Germany, the event would be marred by the horrific terrorist attacks on the Israeli team. Olympia Park still stands today, not only as a memorial to the tragedy, but even more so as evidence of the lingering triumph of Otto's futuristic genius. Otto's principal contribution to the field of lightweight structures is in the realm of tensile architecture, but his interest in novel approaches to shelter was far broader. Another experimental building type that fascinated Otto was the grid shell. Clearly, Otto's most important realized example of a grid shell building is the Mannheim Multihalle, built for the Federal Garden Exhibition of 1975.
With the Multihalle in Mannheim, I tried to make a larger experiment in compression structure. The Multihalle was not using tension structure. These are structures in compression. I have done several experiments with compression structures, but the Multihalle was the largest.
A grid shell begins as a flat arrangement of flexible structural members that are laid in a checkerboard or crosshatch pattern. Applying forces along the grid's margins distorts its original rectangular shape, resulting in curved forms.
It was quite fascinating because that is really a building which is exactly following the idea of form finding. Multihalle has actually some very close relationship to most of Otto's work, even cable structures, because the Multihalle is primarily synclastically curved, which means in both directions the same curvature. And most of his other work is anticlastic, positive curvature and negative curvature. But both were made out of square meshes, which are initially squares and then become rhomboids to become either anticlastic or rhomboids to become synclastic. So there is a very interesting correlation between synclastic and anticlastic. Both of them are made out of rectangular square meshes which are initially flat on the ground and then deformed in space.
Otto chose wood as the material he used for his grid shells, both because of its relatively light weight and because of its ability to bend without breaking.
Wood is a very good material for lightweight structures which are in bending and compression. Some of the aeroplanes of the last war had been completely out of wood. So we used all these structures to enlarge our picture of living and non-living nature.
As he had with his tensile designs, Otto used his time-tested inverted models to find the particular forms he could use. The specific character of these forms was determined through the forces of gravity acting on the suspended chain models. The results of all these experimental models was the monumental Mannheim Multihalle.
There's a history of shell structure throughout history. So they have a kind of historic value because they've been translated from the domes of other, the great churches or whatever it is. And it has a kind of a modernist value because it's also very contemporary.
Compression is much more difficult to build as in tension. Tension is always stable. Compression is very seldom stable. This is the main knowledge of our century.
Though constructed for a temporary event, a Federal Garden Exhibition, the Multihalle is still standing in Mannheim in good, if neglected, condition. Sadly, however, it has been periodically threatened with demolition. Otto's ethically driven minimalism means that he hopes to make as small a mark on the earth as possible. In this light, it's not unexpected that Otto would feel that the 1980 Hellebrunn Aviary at the Munich Zoo was his greatest accomplishment. Designed collaboratively with architect Jörg Gribbel, the aviary is barely there, illustrating Otto's unique take on the concept of less is more.
And Frey Otto's work in that vein of less is more is quite spectacular in that the thinness, the delicacy, the intricacy of his design is done with very, very few moves, and it's done with a kind of collaborative and collective sensibility that's quite unique in both premise and in execution. His aviary project is a perfect example where he was able to embrace the function of the building, the necessary performative qualities that needed to happen, and advance his own agendas of structural thinking to find a unique solution that's perfectly suited to it.
It's not like the high tech where it's very visible, but how to make it almost disappear so that the building almost floats.
As an architectural element, it's really a building which is very good example of a architecture in response to nature, because it's a very natural form.
Of course, the aviary is what I like my best art building, architectural building. As a visitor, you forget that you enter the aviary. You have water inside and outside. You see fishes. You have a landscape. In winter, it can happen that the aviary is covered by snow. Then you have a tent out of snow. And very thin wires. And it is a large room. A room which is 100 meters long is not small. So you can really walk through.
For Otto represents a kind of sophisticated and augmented version of the less is more statement, and that kind of reduction to essential requirements is brought to kind of fulfillment in his work and in these processes. Seems to disappear totally. The only accentuation is around the pylon. There's some kind of need to gather the net and build up strength in the net to then let it meet the pylon. Yeah, but it is beautiful. The aesthetic I would talk about he's bringing forward is an aesthetic of variation, organic variation, like you find in nature. It's an aesthetic of lightness and dematerialization, so the sense of a light footprint.
The aviary clearly represents the culmination of Otto's lifelong interests in reconciling nature with architecture. And the aviary succeeds on both of these accounts. It represents both a brilliant solution to the special enclosure needs of an aviary and, at the same time, the novel and expressive modernist shapes of the structure obviously derive from the forms Otto found in nature. Most remarkably, the aviary actually seems to vanish and melt into its natural setting. Strolling along the meandering paths, visitors genuinely experience a walk through the woods. The sights and sounds of nature flow seamlessly from the outside, literally uninterrupted, right through the aviary. In addition to his dual careers as an architect and engineer, Otto was also a lifelong educator. Beginning in the 1950s, he taught and presented workshops at colleges and universities in Europe and in the United States. Soon after earning his doctorate at the Technical University in Berlin, Otto, in 1958, founded the original Institute for Lightweight Structures. In 1964, the institute was relocated to the University of Stuttgart, where Otto had joined the faculty. He served as the institute's director until his retirement in 1990. At the institute, Otto pioneered alternative teaching methods that often relied on experimentation, observation, and actual construction practice.
It's very hard to identify a greatest accomplishment of some very general inventor like Frei Otto. I would say a great accomplishment was the institute at the university in Stuttgart and influencing a whole generation, several generations of engineers towards a very innovative approach to structural design, to architecture, and so on.
Well, he was never teaching in the normal way. We never had permanent and regular lectures in our institute.
I was a student in Stuttgart while he was teaching and while the institute was going on. It felt like hippiedom. The institute was full and overgrown with vegetation plant, and scientists looked like hippies. We were the early 80s, we had totally changed our kind of aesthetic sensibility, and this seemed, so that blinded me a little bit about the profundity.
He has an incredible feeling for the flow of forces in a structural system. He can feel what is the best way, without any calculation, feel and describe. That's also necessary to describe it, to communicate to others, which then do a perfect calculation.
He crossed the border between pure engineering, where engineering is pure mathematics science, to a design approach to engineering.
And that was important for me because I was educated as just a simple civil engineer based on calculation. And that is what I had to learn my first time working with him, that there are many other aspects which cannot be calculated.
The Institute of Lightweight Structures has always been very influential since Frei Otto founded it. It developed new methodologies, and this institute actually opened the discussion between the architects and the engineers. Suddenly, engineers were empowered to discuss formally with architecture.
The Institute is still housed today in a tent structure that served as an experimental study model for the German pavilion in Montreal. Antonio Gaudí, who worked in Spain at the turn of the 19th century, was a key influence for Otto. Gaudí's approach to form finding through experimentation provided Otto with his only modern predecessor.
Of course, Gaudí is one of those men my institute and with my students studied very deeply. We are real knowers of Gaudí's work and admiring it. We even made a repetition of his famous model, which is still in the basement of the Sagrada Familia in Barcelona. But is this a whole story? We could talk hours on Gaudi.
Gaudi was somebody who pioneered the chain hanging models, a kind of early form finding, but Fra Otto systematized and expanded that and generalized that research.
Gaudi, everybody before had to work with the ideal parabolic form. Fra Otto was able to change these forms, create asymmetric parabolic forms. So he carried it further.
Fra Otto looks towards nature, but not from the kind of conventional discourse, which tends to be biomimicry. He looks towards nature to find natural processes and intrinsic physical forces and natural forces that have an essentialism to them.
Form finding is a physical setup apparatus which settles into a form according to the weights and forces and orientation he sets that model against gravity. So it is working with elastic fabrics, for instance, and hanging weights on them, or chain models. Media like soap, where form self-organizes and it's not drawn by hand or invented or preconceived. It emerges out of a physical process. It's just something you let a natural physical process take place, and sometimes these setups are such that they are settling into an equilibrium form. And the good thing about these forms is that they are self-optimizing and equilibrizing relative to the forces. So when he's doing his hanging model, where a form settles, and he's photographing this and freezing this and then inverting it, it is an optimal dome shape. And that could be on a totally irregular footing, so it's a complex, irregular, settled form like for the Mannheim, but it's ultimately self-optimizing, and when he then flips this over, he has a beautifully reliable shell structure, which would have been impossible at the time to calculate because of its irregularity of form.
And it's tremendous as an idea of a sort of utopian idea about knowledge and the potential of architecture to affect the broader culture and community that we live in. I think that's fundamental to Fra Otto's work, is not just the formal and the functional aesthetic that he derived, but also the social and the pedagogical agendas that he tried to pursue and really make almost open source, kind of accessible to everyone. It really was a vision for a new way of thinking about architecture.
It's the paradigm shift, and that these forms are appealing, attractive, sensuous, beautiful, legible, plays into that, of course. The results need to also convince intuitively and become striking, but they have more depth and they have this kind of lightness, this material efficiency, and that paradigm, I think, is very, very important, which really inspires what we're doing now, can be expanded beyond structural criteria into environmental criteria. Energy, sunlight penetration, water management, where we need to have that similar open-mindedness about morphologies emerging out of these simulations, form-finding processes.
What has re-emerged through, not only because of computing, but through computing, a lot of these experiments were refound again.
What I find so powerful about Frau Otto is that his research paradigm can't be reduced to tensile structure. It's a general new way of approach to all architectural and urban morphologies. And I think all that was initiated by this shifted perspective which Frau Otto introduced into the discipline. And that's why I find him so inspiring and so path-breaking.
With the rise of digital technology in the last 20 years, Otto's ideas are more important and relevant today than they were over a half-century ago when he first began to develop them. Otto continued his practice into the 21st century, working chiefly as a consultant. His expertise was sought out by a number of younger architects, including Shigeru Ban, who conferred with Otto on the design of the Japanese pavilion at Expo 2000 in Hanover. Over the course of Otto's long and distinguished career, he sought not so much to determine the forms of his buildings as to discover them through experimentation. When considering his most important projects in retrospect, it's clear that Otto's work traced a singular trajectory that followed his relentless quest to establish a nature-based architecture. On March 9, 2015, while this documentary was still in production, Frei Otto passed away. However, before Otto died, he had been informed that he was being named the 2015 laureate of the Pritzker Architecture Prize, which was awarded posthumously.
To understand living structures, especially those which are not stable, of those which can move, which can live. We have now the future. The future is not tomorrow, the future is today. And we have to see all these evolution in a whole. And you have a picture of the world of tomorrow.
Otto's contributions to architecture, engineering, and education are ongoing, having impacted his own time, the present, and spanning the future.
Now we are at the end of the broadcasting, the conference Architecture of Lightweight Structures, organized by Studio of Membrane Architecture, Department of Architecture, Faculty of Civil Engineering, Czech Technical University in Prague. We have seen 15 nice presentations from the lecturers of many different countries all over the world. As Czech Republic, Slovak Republic, Austria, Germany, Belgium, South Africa, Canada, USA, Mexico, and Chile. I would like to thank you all for your attention. Thanks to all participants. We did really enjoy the broadcasting with my colleagues here in the studio. There are my colleagues.
Hi.
Okay. We hope meeting you next time face to face. Thanks again and goodbye.